Hello everyone. In this video, we are going to provide complete solution of TFR 2023 paper. So I'll be providing solution of most of the part and Amit sir is providing solution of electronics part. Okay. So let's start with part C. After part C, we'll do part A and then after that we'll do part B. Okay. See, this question is related to mapping from Z plane to omega plane. It says some function f of z is mapping this triangle in Z plane into another triangle in omega plane. So question is which of the following cannot be function fz. Okay. So here obviously there are various possibilities for fz. So there is no need to find fz. Instead of that, what we can do is we can check the correct options, because if one option would have been correct, then we would have tried to find fz, but there are more than one options correct, so it is better to check options itself. Okay, so let us say start with option D, for example. Okay, so option D, it is fz is given to be 2z plus 1. So let's see whether this function transforms this triangle into this triangle or not. Okay, so what I'll do is see, there is a point in z plane -1. So let's see which this point transforms to which point on omega plane. Okay, so we'll put z is equal to -1 here. Okay, so z equal to -1. If you put here, we get here f of z is equal to -1. If you put here 2 into -1 and +1, so that gives you -1 actually. So we can say -1 is actually transforming into -1 itself. Okay. Now, if you put, suppose z is equal to, let's say we put +1. Okay. It's this one, this +1 we put. Okay. Then we get here f of z is equal to 2 into +1 or +1, 2 into 1 +1, so that is 3. And now if you put z is equal to, yeah, z is equal to this one, √3 iota, then f of z will become equal to, here if you put √3 iota, it will become 2 √3 iota plus 1. So we can say this point is transforming to this point. Okay, 1 plus 2 √3 iota. Okay, so therefore we can say this function is satisfying this situation. Okay, now let's check option A, for example. Okay, so option A, it is f of z is given to be e to the power 5 iota 5 pi by 6 and multiplied by z plus we have 2 iota 2 √3. Let's write like this. Okay, now you see we can write this function as e to the power iota, and we have pi minus pi by 6. Okay, and here we have z plus iota 2 √3. Sorry, 2 √3. Okay, so this e to power iota pi, that gives us -1, and e to power minus iota minus pi by 6 gives us cos pi by 6, which is √3 by 2, and minus sin pi by 6, so that is 1 by 2. Okay, so iota sin pi by 2, so that is iota 1 by 2. This is what we have. And here we have z plus iota 2 √3. Now let's see. Suppose we put here z is equal to 1. Okay, so if we put z is equal to 1 here, then let's see what we get. F of z is equal to, so we are putting z equal to 1 here, so this minus and minus plus, we get here minus √3 by 2. Okay, and plus this minus minus plus, we get here iota and 1 by 2 plus 2 √3. Now you see there is no such point in this omega plane. See, iota 2 √3 plus 1 by 2. See, highest point is 1 plus 2 √3. Okay, and they see this is minus √3 by 2. Minus √3 by 2 means minus, sorry, this point may be there, but 1.732 divided by 2. All right, so so if I take a negative value, see, divide by 2 it is. Okay, so if I take a negative value of x coordinate, okay, then this is for those negative values, y coordinate is less than actually 2, but here you see y coordinate is becoming more than 2. Okay, so we can say that there is no such point on omega plane. because this is negative. So if you go to negative side, see, on negative side, this is the graph. Okay, so here you can see y coordinate is less than actually 2. Okay, but here y coordinate is becoming more than 2, so we can say that there is no such point on omega plane. So therefore we can say that this function is not satisfying this situation. Okay, all right. So therefore function given in option A is not satisfying this mapping. Okay, now let's do this question. This is a very standard question which is almost given in every book of mathematical physics. See, in this question, you see there is a integration. We have to do this integration. I is equal to dx divided by root x and x square plus 1. We have to do this integration. This is 0 to infinity. So if you put here, put root x is equal to some t, then you get here 1 by differentiate it 1 by 2 root x and dx is equal to dt. So now put root x equal to t here, so you get dx is equal to 2t and dt. That's what you get. So therefore this integration becomes, actually, see, if you put x equal to 0, you get t equal to 0. So, and when you put x equal to infinity, you get t equal to infinity. So limit is not going to change. And here we'll write 2t and dt, and divided by root, in place of root x you can put t, and here in place of x square, if you calculate x you get t square. So in place of x square you get here t power 4. Okay, that's what we are getting, t power 4 plus 1. So t and t will cancel out, and there is factor of 2. So we can transform this integration from minus infinity to plus infinity, and dt and divided by t power 4 plus 1. See, when you do this, because this is an even function, so you can do you can change the limit minus infinity to plus infinity. You'll have to divide by 1 by 2, so that 1 by 2 will cancel with this 2. So now to do this integration, we'll have to, so we'll have to actually use contour in this form, semicircle. So this is infinite contour which is going from minus infinity to plus infinity. Okay, so this is imaginary z-axis and this is real z-axis. Okay, so this is, we can write this integration as minus infinity to plus infinity and z and z to the power 4 plus 1. Okay, so this is z is just a dummy variable. Okay, uh, so we have to do this integration. So for that we need we want to find, this is infinite semicircle in upper half complex plane. Okay, so now to do that we'll have to find singular points inside this contour. So for that we'll put z to the power 4 plus 1 equal to 0. So we get here z to the power 4 is equal to minus 1. So we have z to the power 4 is equal to e power iota pi. Okay, so from here if you calculate roots, values of z, we get here e to power iota pi plus 2n pi and divide by 4. Okay, where n will be equal to 0, 1, 2, 3. Okay, so values of z that we are getting here from here is, if you put n equal to 0, you get here e to power iota pi by 4. Okay, and then you put n equal to 1, you get here e to power iota 3 pi by 4, and then e to power iota 5 pi by 4, and e to power iota 7 pi by 4. Okay, so these are the singular points actually. But in upper half plane, if you check, see the argument is this angle is pi by 4. This is 3 pi by 4. But this is 5 pi by 4 is more than pi. So if you start from here, you get you rotate by pi angle and you reach here. So this angle is more than pi by 4. So that means this singular point will be somewhere in third quadrant. Okay, so that is not within this within this semicircle. So singular points within the semicircle are these actually. These two are the semicircle within the contour. So therefore, we can write like this. Here, value of integration will be equal to this integration 2 pi iota and sum of residues. So residue at z equal to e to the power iota pi by 4 plus residue at z is equal to e to the power iota 3 pi by 4. We have to calculate residues at these 2 points. Okay. Now, you see, these are simple poles actually, residue of order 1. So therefore, we can calculate residue easily as 2 pi iota. Okay, this is in the form of fraction. So there is a numerator, there is no denominator. Numerator is 1 here in this function, and denominator is z power 4 plus 1. So when we have a function of this form, we know that p of z and divided by q of z, then to calculate residue at simple poles, we can just simply write it as pz and divide by p prime z. Sorry, q prime z. Q prime z. So that is the formula for residue. So if you do that here, you will get here 1 by differentiate this denominator. You get here 4 z to the power 3. So we'll put z equal to this much. So you get here e power 3 iota pi by 4. Plus here also you will get p is 1 actually here in the denominator, and q is q primed. If you differentiate this one, you get here 4, and z to the power 3 you will get. So z we are putting this one. So you get here e power iota and 9 pi by 4. Okay, this we get. So here 4 will come outside. You get here pi iota and divide by 2. And this we can write as e to power minus 3 pi by 4, and plus this we get e to power minus iota 9 pi by 4. Okay, so therefore we can write it as e to pi iota by 2, and this is in third quadrant actually. So if you calculate it, you get here minus 1 by root 2 and minus iota 1 by root 2. Okay, that's what you get. This you can simplify as e to power minus iota 8 pi by 4. You can write like this, and e to power minus iota pi by 4. So 8 plus 1, it becomes 9. Okay, so this is in fourth quadrant actually. Okay, this one is in fourth quadrant, and this becomes 1 actually. It power 2 pi iota is 1. Okay, so this is 1. So you get here pi iota and divide by 2, and this is minus 1 by root 2 and minus iota by root 2, and here this is 1, and this gives you basically it is in fourth quadrant. So this is cos pi by 4. Cos minus pi by 4 is actually 1 by root 2, and here minus iota by root 2. That's what you get. Okay. I think here I made a mistake. Let me see. E to power minus 3 pi by 4 we have. So this is in, so we can write it as e to power minus iota pi by 4, or e to the power iota, or we can write plus and here minus iota 4 pi by 4. We can write like this, right? So this becomes actually, yeah, so minus. So this becomes minus 1, and this gives us 3. It is all right. Oh, sorry. Here there was no minus, there was plus sign here actually. Okay. So we get here. All right. So therefore this one and this one will cancel out, and these two will add. Okay. So we'll get a factor of 2. Okay. So 2 and this 2 will cancel out, and root 2 will remain here. So we'll get iota square will give you minus 1. So now you just add, and you will get here pi by root 2. That's the answer. Okay. All right, so I had made a mistake here. So I had written minus sign. That's why it was giving wrong answer. So the correct answer is pi by root 2. Okay. All right, so let's move to another question. See, this is a question from classical mechanics. It says that there is Hamiltonian given, and now we are transforming this Hamiltonian using this generating function. So we have to find the new Hamiltonian new coordinate. So let's write the differential relation for this generating function. See, differential relation here is del f by del, it is function of q. So if you differentiate it with respect to q, you get p. So now you differentiate this generating function with respect to q. You get here m omega and q, and here you get cot capital Q. All right. So therefore, that's what we have. So let's call it equation number 1. Okay. And now another differential relation will be del f by del capital Q, because it is function of capital Q with negative sign. This is equal to capital P. So when you differentiate capital Q, you get minus cosec square Q. So minus, and this minus becomes plus. So you get here m omega and Q square by 2. And here you get cosec square capital Q. Okay. Cosec square capital Q. All right. So from here you can get value of Q, which is 2 capital P and divided by m omega. Okay. And here you get sine square capital Q. So this is a value of Q square actually. Okay. So if you calculate value of Q from here, you get here root under 2 capital P and divided by m omega and sine capital Q. This let's call it question number 2. So this Q, let's put this into 1. Okay. So if you put Q into 1, see, this can be written as cos by sine. So sine and sine will cancel out, and 1 m omega will cancel out. So you will get here P equal to 2 capital P is there, and 1 m omega will cancel out. So you get m omega in the numerator, and here you get cos capital Q. So this is the value of small p, and this is small q. Now we know that new Hamiltonian new coordinates is written like this: h plus and del f by del t. Since this generating function is not a function of time, okay, so therefore this term is 0. So you get here h actually. So which is given to be here 1 by 2m, and here p square plus 2m. No, there is not 2m. P square plus m square omega square and q square. Okay, this is what we are getting. Okay, so here we have h prime is equal to, let's put the value of small p from here, and q from here. Okay, so if you put a small p, we get here 1 by 2m, and here we this root will go, so we will get here 2 capital P m omega, and here you get cos square capital Q plus this is m square omega square, and now you put the value of small q, which is here, so we get here 2 capital P and divided by m omega, and here we get sine square capital Q. Okay, so therefore we get here 2p cancel mm cancel out, and you will get here 2p m omega, and here also you have 2p m omega. So 2 and 2 will cancel out, and m will cancel out. So therefore p and omega will come outside, and here you get cos square capital Q plus sine square capital Q, which is 1 actually. So basically we are getting omega multiplied by p. Okay, so that's the answer, this one. So option A is correct actually. Okay. Now so this was a very systematic question. Actually, this question is solved in all books of classical mechanics, including Goldstein's book also. Okay. Now let's see this question. This is somewhat new question. It says a simple pendulum is oscillating freely in the vertical plane if the string is shortened. If a string is shortened very slowly to half its length, angular amplitude theta max will change by a factor. So we have a simple pendulum. Let's see. There is a simple pendulum. It is oscillating like this. This length is suppose L, bob, mass of the bob is M. Suppose we take this as potential energy 0 level. Okay. So now it is oscillating. So if you want to write Lagrangian, you will get here kinetic energy, which is half m, and v square velocity is L theta dot r omega basically. So velocity is L theta dot like this. So you get here half mv square, and potential energy will be kinetic energy minus potential energy we are writing, that will be minus mgl cos theta. Okay, this depth is actually L cos theta. So we have taken reference level here. So that's why potential energy is minus mgl cos theta. So Lagrangian we have half m L square theta dot square and plus mgl and cos theta. That's the Lagrangian. Okay. Now you see here length is being shortened very slowly. So in such processes, actually action variable is constant. So action variable is written like this: p theta d theta integration. Okay, let's say 0 to theta max. This integration is actually constant here in this process. Okay, so here p theta, if you calculate, p theta is equal to, this is generalized momentum, del L by del theta dot. So this is coming out to be ml square and theta dot. Okay, so let's put it here. So we have ml square is, you will, since ml square we are integrating with respect to theta, so I'm taking L outside. Now here we have theta dot and d theta. So this is constant actually. Okay, now see, this is a it says it is oscillating, but we'll assume that, see, to make this calculation simple, we'll assume that this is small oscillation. Okay, so let's assume a small oscillation. So we'll say for a small oscillation, motion will be simple harmonic. Okay, this is SHM. So in SHM, you can get theta dot is equal to omega root under this theta max whole square minus theta square. Okay, so for SHM we have this. Okay, where omega is angular frequency, which is this omega is root under g by L actually for simple pendulum. All right, so let us put this here. We get ml square, and in place of theta dot, when you put this, you get here root under g by L, and here root under theta max square minus theta square. And now we are integrating with respect to theta, and limit is 0 to theta max. Okay, and this is constant actually. We are writing this as constant. Now we don't have to do this integration. We can just infer the conclusion from here. See, we have m and L power 2 minus 1 by 2. So that is actually 3 by 2. You combine these two and you have root g here. And from here, what you do, take theta max out. So we will get here a theta max term. And here we get 1 minus and theta square by theta max square. Okay, and d theta. And that is equal to constant. Okay, and limit is 0 to theta max. Now what you do is introduce a dimensionless variable. Let us introduce a dimensionless variable, theta square by theta max. Sorry, let's put theta by theta max is equal to, let's say, some y. So therefore theta will become y and multiplied by theta max. Okay, and if you put theta equal to 0 here, you get y equal to 0, theta equal to theta max, you get y equal to 1. So this integration will transform to this integration, ml power 3 by 2 root g, and here you get theta max. Okay, and when you put d theta, see, d theta will be equal to actually theta max and dy. Okay, so here when you put d theta, theta max into dy, another theta max you will get. So you get theta max square here. Okay, and integration will transform into 0 to 1 and root under 1 minus, and this will be just y square and dy. Okay, so that is actually constant. So when you integrate this one, you get just a number. Okay, so therefore we can say that L to the power 3 by 2 and theta max square, that is constant here. Okay, that is constant. So therefore you can say like this, we have L to the power 3 by 2 and theta max square is equal to constant. Other terms are constant actually. Here L is being varied, so therefore theta max is changing. So that's what we have to find. So theta max will be equal to some constant and divided by L to the power 3 by 4. Okay, so if you change L to L by 2, you shorten the length by half. So theta max will change to here, you will get half to the power 3 by 4. So that 2 factor of 2 will come in the numerator. So 2 to the power 3 by 4 multiplied by theta max. So whatever earlier we had theta max to be equal to, now that theta max gets multiplied by 2 to the power 3 by 4. Okay, so that's the answer. Okay, so therefore correct option is option A. Okay, so this was a question related to adiabatic variation in which action variable remains constant. Okay, let's move to another question. See, this is a question from quantum mechanics on variational principle. It says Hamiltonian is given. Now we take variational wave function to be equal to this, and we have to. So question is, what should the value of lambda should be chosen as for to estimate ground state energy? What value of lambda we should choose? Okay, so we know that in variational principle we first calculate the expectation value of Hamiltonian, which gives us energy. So which is expectation value of Hamiltonian. So we'll calculate it as a psi star, and here h psi and dx, and divided by, so this wave function is not normalized, so we have to divide by this term. Okay, this we have to calculate. So when you calculate this, so let us evaluate all the terms one by one. Okay, so size, this denominator we are calculating here. So we have this psi star, psi, and dx. This limit will be from minus infinity to plus infinity. Okay, so because here limit is also given to be minus infinity to plus infinity. So this will become basically e to the power minus 2 lambda and x square or dx, minus infinity to plus infinity. Okay, now you see this integration is given actually here. See, e to the power minus lambda x square and multiplied by a, that is given to be here a. So we don't have a here, so this will be equal to 1 multiplied by root under pi by lambda is given here. Okay, but in our integration in place, see here lambda is there in integration, but here in our place 2 lambda is there, so we'll write here 2 lambda. So this integration will be root under pi by 2 lambda. Now let's calculate, when you calculate expectation value of Hamiltonian, you will be calculating its expectation value. So let us calculate its expectation value here. So we are calculating this term psi star, and here we have a x square and psi and dx, minus infinity to plus infinity. So you have a, and then you have x square and e to power minus 2 lambda and x square and dx. Okay, because psi is equal to e to power minus lambda x square. So when you put it to, in two places, you get e to power minus 2 lambda x square. Okay, this limit is from minus infinity to plus infinity. Okay, so here we have a, and now this kind of integration is given here. E to power minus, see b term is not there. Okay, but x square multiplied by this e to power minus lambda x square. So again we have there is lambda here, but in our integration we have 2 lambda. So we'll use this. We'll get a factor of 1 by 2. Okay, and root under pi divided by, it is lambda cube, so we'll get here 2 lambda ka whole cube. Okay, this we get. Now we have to calculate expectation value of this term. So we have p square by 2m, and we have psi star and psi and dx integration, minus infinity to plus infinity. So this can be written as, you put p equal to minus h bar square by 2m, p square. So if you calculate, this can be written like this, h square by 2m. See, this is double derivative, but using by parts integration, we can convert into single derivative. So this actually becomes d psi by dx. Okay, modulus whole square and dx, from minus infinity to plus infinity. This you get. So here we are getting h bar square upon 2m, and here d psi by dx. So when you differentiate this term, okay, you are going to get a minus lambda, but there is a square, so you get lambda square, and there will be 2x term coming out, so you will get here 4x square. Okay, and again e to power minus. That's what we are going to get, right? Yeah, I made a mistake actually, sorry. There it was actually ax to the power 4. So here we had 4. Okay, so now here we have 4. So if there is 4 terms, so we'll have to use this one, x to the power 4 integration. This is 3 by 4, sorry. So this will be 3, and here it will be 3 by 4. Okay, 3 by 4, and this is pi and lambda to the power 5. So here we'll get 2 lambda to the power 5. Okay, that's what we have. Now here we are getting x square. Here this will be 2 lambda x square. Okay, and dx. This integration is from minus infinity to plus infinity. See, this is a very well known thing. When you are calculating expectation value of p square by 2m, this is written like this. Okay, because double derivative that you get from p square can be converted into single derivative by using by parts integration. Okay. So now we have done the differentiation, and after differentiation we squared it and we are getting this term. So let's write here h bar square upon 2m, and here we have a 4 lambda square outside, and we have x square now. So x square term integration was this one, second one. So we have 1 by 2 here, and root under pi divided by 2 lambda whole cube. Okay, so there was a slight mistake here. There was x power 4. So that got noticed because we were getting x square here. All right. So let's cancel the common terms. See, 4 cancels out. So we get here h bar square, and this h bar square and lambda square we are getting, and there is m. 4 cancel out, and we get here pi and divide by 2 lambda whole cube. That's what we have. Now, so we have gotten these terms. So we are going to write this expectation value of Hamiltonian. So let's see. Here we have E equal to psi star h psi and dx, and divide by integration psi star psi and dx. So when you calculate this, basically you are calculating expectation value of p square by 2m and expectation value of ax square, which we have calculated here already. So let's write it 3a by 4. We have here 3a by 4 and pi divided by 2 lambda to the power 5, plus we have here h bar square lambda square by m. This is h bar square lambda square and divided by m. Sorry, divided by m. And then we have root pi divided by 2 lambda whole cube. And in the denominator, we had this one. So this is pi by 2, root under pi divided by 2 lambda. So let's cancel the common factors. See, root pi is everywhere in numerator and denominator, that will cancel out, and 1 root under 2 pi will also 2 lambda will also cancel out. So root under 2 lambda to power 4 will be left here, and when it comes out of this root, then we get 2 lambda to the power 2 actually. So you are getting here 3a by 4 and 2 lambda to the power 2, plus here you will get h bar square lambda square by m, and here you will get 2 lambda only. Okay, that is energy. So let us minimize energy with respect to lambda. So here we have 3a divided by 8 lambda square, and plus h bar square we have, let's write it, h bar square lambda square, and divided by we have 2m and lambda. That's what we have. So let's minimize it with respect to E. So we want to put this dE by d lambda equal to 0. If you put this 0, you get here from here minus 3 into 2a and divided by, that's what we get, right? Okay, so we are getting here 3a by 8, 3a into 2 or divided by lambda cube. And here, since 1 lambda is cancelling out, we get here h bar square upon 2m, okay, into 1, because only lambda is there. So that's what we have gotten. So 2 will cancel with 8, we get here 4. Okay, so therefore we are getting here 3a divided by 4 lambda cube with negative sign, plus h bar square and divided by 2m, that is equal to 0. Sorry, I made a mistake. I think here there was 2 lambda whole square, so it will be 4 and 4 16. So one factor of 2 I have missed here. So you are getting a factor of 2 also here. Okay, it will become 16 actually. So I have written here 8, so that was the mistake. So now here we have extra factor of 2. So here there will be extra factor of 2, so this 2 and 2 will cancel out. Okay, so therefore minus 3a divided by, calculation part you can check yourself. So we are getting 2 and 2 will cancel out, 4, and here lambda cube and plus h bar square and divide by m, that is equal to 0. So therefore lambda will be equal to, okay, from here we can calculate lambda is equal to 3m into a, this 3m into a, and divided by 4 h bar square, this whole power 1/3. That's what we are getting. Okay, that's what was given in option, I think, 3ma divided by 4h bar square, that's right. Okay, so there was some calculation mistake here and there. You can check those calculations. Okay, this was very straightforward question on variational principle. Okay, so these are not conceptually difficult question. Okay, now let's move to another question. See, this is a quite simple question from radiation. It says that an electron is revolving. So when an electron is revolving, it is actually accelerated. And you know that when an electron is accelerated, it emits power, which is given by Lama formula Q square A square upon 6 pi epsilon naught and C cube. Okay, so A for circular motion is given by omega square r, where r is, here r is given to be a, here this a is acceleration, यहाँ पे जो हम a लिख रहे हैं that is acceleration. Okay, not the radius. Okay, for radius I'm using r. So here if you put this a over here, obviously p will be proportional to omega to the power 4. Okay, because omega square हो जाएगा, you will get here omega to the power 4. So therefore that is quite straightforward. Okay, its correct answer will be option A. Now it says for an electromagnetic wave propagating through a rectangular waveguide, the electric and magnetic field. See, actually, we will assume that this is a hollow waveguide. We know that in hollow waveguide, transverse electric magnetic mode (TM) mode doesn't exist. TM mode doesn't exist. Okay, so that's why we say that they are never transverse. Electric magnetic means both electric and magnetic fields are transverse to directional propagation and perpendicular to each other. Okay, so that's why we say that these are never perpendicular to each other. Okay, now let's discuss. So therefore correct option for this one is very straightforward. This is not a numerical problem but a theoretical problem. Okay, so this is directly from theory. You can check in Griffith's book, it is mentioned there also. Okay, now let's move to this problem. So this is a problem, it is not a question directly from theory. It says consider a fermionic system with Hamiltonian. Consider grand canonical ensemble for this system at temperature T and zero chemical potential. Kb is Boltzmann constant. The grand canonical partition function of the system is given by, we have to find grand canonical partition function, and chemical potential is given to be 0. Okay, so here this Hamiltonian is given. What you can do is you can calculate its eigenvalue. So that I'm not doing here. You can calculate eigen value of H. So if you do that, you will get here minus root 5 E naught 0 and root 5 E naught. So 3 eigenvalues you get. Okay, so basically we can say there are 3 energy levels. So among these 3 energy levels, we have to distribute particles, and these are fermionic particles. So we'll assume only one fermion will go to one energy level. Okay, we are assuming it to be spinless fermion. Okay, so let's say, so we have this kind of situation here. We have energy level. See, let's discuss distribution of particles in energy level. Okay, distribution of particle energy level. See, energy level is here. Let's say 0 minus root 5 E naught and root 5 E naught, and let's say we are getting total energy. This E is total. Okay, so we have this kind of situation. But since it is grand canonical ensemble, okay, so here number of particle is not fixed. Okay, so let's say there is no particle. n equal to 0. So obviously here there will be zero particle, zero particle, zero particle. So no particle is occupying any energy level. So you get zero energy. Okay. Let's say number of particle is 1. Okay. Number of particles 1. So particle 1 can be here. There will be no particle here. So if particle is here, you get zero energy. Okay. Because this energy is 0. Okay. Now, if there is one particle, it can be here. Okay. So if it is here, energy is minus root 5 E naught. Okay. Now, one particle can be here also. So in this case, energy will be root 5 E naught, total energy, because there are no particles. So these energy levels are not occupied. This energy level is occupied. So therefore, energy of particle is this root 5 E naught. Okay. Now suppose there are two particles. Okay. So one particle can be here, one particle can be here. Okay. And no particle here. So in that case, energy is minus root 5 E naught. Okay. Now, two particles. So there are two particles. So these can be here and here also. So if particle is here, total energy will be root 5 E naught. Okay. Now, two particles n equal to 2 particles can be distributed like this also. One particle, no particle here, one particle here, one particle here. So in this case, total energy will be 0. Okay. Now, if there are three particles, n equal to 3, distribution will be like this only. Okay, so in that case also we get zero energy. Okay, because we are getting minus as well as plus. So total energy. Okay, so now we are see total energy we have this type of total energy we have 0 we are getting 4 times. Okay, here 2 times we are getting this one. Okay, minus root 5 E naught, and 2 times we are getting plus root 5 E naught. Okay, so if you write energy and degeneracy, see energy and degeneracy, it is something like this. See, we have energy and degeneracy G. So energy is 0, its degeneracy is 4. And energy is root 5 E naught, its degeneracy is 2. Energy is minus root 5 E naught, its degeneracy is 2. Okay. So these are the degeneracies. All right. So therefore, now if you want to write partition function, we can write it as summation on all energy levels. Okay. See, we have already considered summation on particles. Okay, various possibilities of particle we have considered. When you write a grand canonical function, you sum on particles as well as on energy levels. Okay, so here we have already summed on particles. Okay, so we are summing on energy only. So we have this degeneracy of energy level e to the power here minus beta and e minus mu n. Okay, that's what we have. So here chemical potential is given to be 0. So this term won't be there. So we have e to the power minus beta E only. So let's put here. So when you put E equal to 0, you'll write G equal to 4. So you get here 4 e to the power 0. That is 1 actually. So 4 you get. When you put E equal to this much, you get degeneracy 2. So you get here minus beta and root 5 E naught. And again, for equal to this minus term, you have degeneracy 2. So we'll write 2 here in place of G, and minus, when you put minus here, minus and minus plus, you get, so 5 E naught and root 5. That's what you get actually. Okay. So now this term simplifies to 2, and this is e to power some positive term, e to power minus negative term. You can divide it by 2 and multiply by 2. So you will get here 4, a factor of 4 and cos hyperbolic. Okay, and root 5 E naught multiplied by beta. That's what you get. Okay, so here actually beta is 1 by kBt. Okay, so it is this is what we are getting actually, but we are not getting any of the options given actually. So here all options are wrong. There should have been a bracket, actually one here written, 1 plus, and it should have been like this. Okay, so correct, none of the options are correct. Correct answer is this one actually. Okay, so this is an electronic question which will be discussed at the end of this video by Amit sir. Okay, now let's see this question. It says in an experiment that measures angular distribution of emission of particles, angular distribution function is given by this formula, where n theta is the number of particles detected at angle theta. If for a certain sample we count n and n at pi by 4 is 16,265, and this is 8192 at any theta equal to pi by 2. Okay, then uncertainty we have to calculate. So we have, see, only two data points, and out of those two data points we have to calculate uncertainty. So I actually don't know how to do it, but somehow I figured out to estimate the this uncertainty. See here, there is a relation when theta, you put theta is equal to pi by 4, and when you put theta equal to pi by 2, see, this number is actually just twice of the sorry, this number is just twice of this number. If you divide this one by this, you get something 1.9 or something very close to 2 you will get. Okay, so we can approximate this function as, see, this function, this is a function of theta, and when you increase theta from pi by 4 to pi by 2, it is actually becoming half. Okay, so we can think of approximating the function. So I thought of it like this. Okay, this function will be something of this form. This n theta will be of this form. So this f will also become a function of theta. So it can be written like this: 2 cos square theta. Okay, now you put here, see, theta equal to pi by 2. If you put, you get 0 here. So 0, so you get only factor of 1. Okay, but if you put theta equal to pi by 4, you will get here 1 by 2. 1 by 2, 1 by 2 will cancel out, and you will get factor of 2. So at pi by 4, you are getting 2 here, and at pi by 2, you are getting 1. Okay, so this function roughly satisfies this condition. Okay, so using these two data, we have approximated the function. Okay, now you see here, df, if you calculate df by d theta, you get here 4 f naught and cos theta and sin theta. There will be negative sign also, but that negative sign I'm not writing. Okay, now divide the two. Okay, so df, if you write, we can erase this. If you calculate just df, you will get d theta term also here. So now let's divide the two. So df and by f we can write. So if you divide the two, f naught will cancel out, and you will get here cos theta sin theta 4, and divided into d theta and divided by 1 plus 2 cos square theta. Okay, this we are getting, but this we have to evaluate at pi by 4. So df by d theta evaluated at pi by 4 will be equal to, let's put pi by 4 everywhere. So you will get here 1 by, so 4, and here 1 by root 2, 1 by root 2 will give you 1 by 2, and here when you put pi by 4, you will get here 2. Okay, so and d theta we have. So ultimately you are getting d theta only. Okay, so df, sorry, this is not df by d, it is not df by d theta, it is df by f actually. So this is df by f, we have calculated pi by 4. So df by f at pi by 4 is only equal to d theta. D theta is basically, you can say, uncertainty in theta. See, theta we are measuring from, so theta, suppose you are measuring angular distribution, so we can roughly think it of 1 degree. Okay, see, we are measuring angle, so uncertainty can be of the order of 1 degree, so which will be in radian. If you calculate, it will be pi by 180. Okay, so that is the value. Okay, so if you calculate its value, it will become something 0. You can calculate it. Okay, let me see what we are getting. I think it is 0.017 or something. So pi divided by 180. Yeah, this is 0.017. Okay, so therefore if you multiply it by 100, df by f into 100, you get here 1.7%. So that is the uncertainty, this uncertainty. Okay, so this is what I'm getting. Okay, so closest answer is this one. Okay, option A. No other option is close to this. Okay, so this is very crude approximation, okay, by which I have solved this question. Okay, there might be some more appropriate method, but I was not able to figure out. Okay, so now let's discuss this question. The energy gap between n equal to 1 and n equal to 2 energy level of hydrogen atom is denoted by E naught. Now consider muonic carbon ion. Okay, so there is a carbon ion which is basically trapping a muon. particle instead of electron. Okay, so we have this kind of situation. We have hydrogen atom, so we have a proton. This is mass of proton, and there is electron revolving around it. And now we have carbon nucleus C plus 5. So here we have uh, this is carbon. So there will be actually nucleus here. So there will be 12. We can say 12 here. Mass will actually, there are six neutron and one proton. Sorry, six proton. Six proton are there. Okay. Now, so therefore we have now this kind of situation. There is a muon. There is muon which is revolving around it. Okay. Muon is revolving around it. Now, so in this case, there is transition from n equal to 1 to n equal to 2. In this case, there is transition from n equal to 3 to n equal to 2. Okay, so question is the energy emitted. यहाँ पे energy जो emit हो रहा है और यहाँ पे the energy of photon emitted in transition from this will be approximately. Here in this case, energy emitted जो यहाँ पे transition से जो energy emit हो रहा है, that energy is E naught. So here we have to tell what is that energy. Okay, all right. So that's what we have to calculate. Okay. So energy emitted, if you calculate, this is this E naught. There is a formula, Balmer formula actually. So this is R infinity and HC, and here you get Z to the power. Okay, we get Z square, and then reduced mass divided by mass of electron, and then 1 by n in final square minus 1 by n initial square. This is the formula. So for hydrogen atom, if we write hydrogen atom, we get here E naught is equal to R infinity, Rydberg constant, Hc, and Z is 1 square, and mu, if you calculate mu, it for hydrogen atom, there is proton and electron. So if you calculate mu, you get roughly mu to be equal to mass of electron. Okay, so reduced mass. Okay, reduced mass we write like this. See, mu is m1 into m2 and divide by m1 plus m2. So for electron and proton, if you calculate reduced mass, you get something like this: mass of electron and then mass of proton, and divide by mass of electron plus mass of proton. Here, mass of proton, you know that this is around 1840 times mass of electron. Since it is very heavy, mass of proton is very large compared to mass of electron, you can neglect mass of electron from here. So mass of proton will cancel out, and you will get mass of roughly reduced mass to be equal to mass of electron. Okay. So here now we have n 1 by n. One is final level is from 2 to 1 actually it is coming. So final level is n equal to 1, and here you get 2 square. That's what we have. Now for C plus 5 के लिए अगर हम calculate करते हैं, suppose this energy of photon is, we calculate here R infinity and Hc, and here Z, in place of Z we'll write 6 because there are 6 proton. So 6 square, and reduced mass if you calculate. So here reduced mass will be calculating. Here there is muon. Okay, and mass of muon is given to be this is 210 times mass of electron. Okay, so in reduced mass formula we'll have to write like this: mu is equal to mass of muon. We'll have to write here in place of m1, which is 210 times mass of electron. Okay, and in place of m2 we'll have to write this mass of this nucleus, so which is 12 times approximately 6 neutron 6 proton are there. Mass of neutron proton are almost same, so this is 12 times mass of proton, and mass of proton itself is 1840 times. So we'll have to write like this. Here 12 is coming because there are 12 nucleons, and mass of each nucleon is 1840 times mass of electron, something like this, and divided by, then we'll have to write m1 plus m2. So in place of m1 you get 210 me or plus 12 into 1840 mass of electron. So you get something like this. Okay, we have this situation. Okay, so now you can calculate this 210 multiplied by 12 multiplied by 1840 me. Okay, and here also 210 plus 2 12 into 1840 ME. You can calculate this. Okay, so in place of M1 M2 we have just written, we have written mass of this, ये इसका mass जो M2 हम लोग लिख रहे हैं, this is 12 times mass of proton approximately. So this is 12 times mass of proton is 1840 mass of electron. Okay, and this is M1, this we are writing. So in place of M1 M2 you just have to put this. Okay, so when you calculate it, it comes out to be approximately 208 times mass of electrons. Okay, so we'll put here 208 times mass of electron and divide by mass of electron. Okay, and here we transition is from n equal to 3 to 2. So here we get here 2 square or minus 1 by 3 square. Okay, so now just divide the two. Okay, so what you get here is E divided by, see, if you calculate, we get here E divided by E naught to be equal to, common factors will cancel out. Okay, so here you get 36 multiplied by 208. This is 36 and this is 208. Okay, and from here you get 9, 1 by 4 minus 1 by 9, so you get actually 5 by 36 from here, and from here you get actually 4 minus 1, so 3 by 4. So when you divide you get here 4 by 3. I think that's what you are going to get. Okay, I think no other factors there. So this 36 cancel out. Okay, so you get here 208 multiplied by 520, or 5 into, we are writing 4 by 3. So that's what you get. So see, these two multiply and give you 1040. Okay, and multiplied by this one, so it will be something more than 1000. You can calculate, it comes out to be close to 14. It gives you perhaps 13. I have done the calculation, 1386. Okay, so that is closest, it says approximately. Okay, so closest answer will be this A option. Okay, so here you get E is approximately equal to 1400. Actually you get E equal to 1386 multiplied by E naught. Okay, so this we are writing closest to 1400. Okay, so that's the correct answer. This is a very basic question related to hydrogen atom. Okay, you can say this was a question on Bohr model also. All right, now this is a question from statistical mechanics. It says we have to calculate, ignoring interaction between atoms, average magnetic moment. Okay, so there is magnetic field and there is magnetic moment. Okay, so in this case, if you calculate energy, okay, uh, energy will be equal to minus mu dot H. So it is a three-dimensional case. Okay, this is a magnetic moment of an atom, so it can orient in any direction. This is like classical. Okay, um, classical dipole. So this is minus mu H and you get here cos theta. Okay, it is like classical dipole. Okay, so therefore this is the energy. Now if you write here expectation value of magnetic moment. Okay, want to write expectation of value of magnetic moment, then we can write it as this is mu. So in the direction of magnetic field, we are calculating expectation value of magnetic moment. This is Z component of magnetic moment actually. So this is mu cos theta. And here we'll get probability term, which is e to power minus beta E and divide by partition function. Okay. And we'll integrate it on solid angle. Okay. So that's what we get. So therefore, here we get mu cos theta e to power minus beta E, and Z we write it as e to power minus beta E. Okay. And this also there will be integration on solid angle. Okay, there is integration on solid angle. Okay, this is mu Z expectation value. All right, so let's put the value of mu here, sorry, value of E. So we get here expectation value of mu is equal to integration, and here we have mu cos theta e to the power minus, this becomes plus actually, beta, and when you put this mu into h, okay, and this solid angle if you put, you get here sine theta d theta term, and here you have e to power beta mu h, okay, and cos theta also there. There is cos theta term in energy, there is cos theta also, beta mu h cos theta, and here you get sine theta and d theta. Okay, so this we can simplify. There is mu cos theta term here, so we can write this as d by d of, here see this mu and cos theta is coming out, so we can differentiate it with respect to beta and h. Okay, so if you, so you can write it like this, ln of integration and e to the power beta mu h and cos theta, and here we have sine theta and d theta. So when you differentiate this term, see ln will give you first of all this term, okay, and when you differentiate this, since we are differentiating with respect to beta and h, so its coefficient will get will come out here, okay, so that's what we are getting, okay. So now we have to do this integration. Here limit will be 0 to pi in 3 dimension, okay. Now, so to do this integration, what you do is put cos theta is equal to some t. Okay, so we get here d of beta mu h. There is beta mu h only here. There is no d term. Okay, so here we are getting this beta and h. We are differentiating with respect to this. So when you integrate it, you are going to get here. See, we'll put here t. This will become dt. Okay, and limit will change from 1 to -1. So you do this integration. Okay, so first of all, because there will be t term here, okay, and this is dt, from here you will get sine theta d theta is equal to minus dt. Okay, so when you do this integration, coefficient of t will be beta mu h, so beta mu h से हमें divide करना होगा, and here we are going to get some e to the power, in place of t you will put limit 1 and -1, so it will actually convert into cos hyperbolic beta mu h, okay, and divided by, multiplied by 2. Since there is no divided by 2 factor, so we'll have to multiply by 2. Okay, so you can just do this integration and see, you will get this. Okay, now we have to differentiate by beta mu h. Okay, and there is ln term here, ln, so we'll get here d by beta h. We are differentiating with respect to this, so we'll get these factors, ln2 minus ln beta mu h plus ln cos hyperbolic beta mu h. We are getting this. Okay, so now when you differentiate, this becomes 0. Its differentiation with respect to beta mu h will give you 1 by beta mu h. Okay, so we'll get here, from here we'll get 1 by beta h. Okay, that's what we have beta h minus, this is minus actually, this is minus, and plus this differentiation will give us, since this is cos hyperbolic, so it will give you 1 by cos hyperbolic and then sine hyperbolic. Okay, so this will give you tan cot hyperbolic 1. So sorry, here we will actually, I made a mistake here, we'll get a sine hyperbolic term here, because when you put the limit, upper and lower limit, there will be a minus sign in exponential, so you will get here sine hyperbolic. Okay, you'll get sine hyperbolic. Okay, so here we have sine hyperbolic, just a minute, there is sine hyperbolic, I didn't do calculations, that's why I made a mistake. So this will be sine hyperbolic term. Okay, sine hyperbolic. So now when you differentiate this, you will get here cot hyperbolic beta mu h. Okay, and since you are differentiating with respect to beta mu h, a factor of beta mu h, mu will come outside here. Okay, so that's what you have. Okay, so we can write this as, see, there is beta mu h term here, so you can multiply here by mu and here also by mu. So mu will come outside, so you are getting mu, and here cot hyperbolic and beta mu h minus 1 by beta mu h. something like this. Okay, so this is a very well known Langevin function actually. Okay, so we have expectation value of magnetic moment is equal to mu, and here cot hyperbolic beta mu h and minus 1 by beta mu h. Okay, so if you do its Taylor expansion, the first term that you are going to get, see, this is of this form, cot hyperbolic x minus 1 by x. Okay, so its first term is actually x by 3. Okay, so here we will get beta, and in place of x you will get this, so beta mu h by 3. Okay, so therefore, oh sorry, there was mu here, there was mu. So this is mu, and its approximation gives us beta mu h x by 3. So the x is this one actually. So mu and b, this becomes mu square and h. Okay, and divide by beta is kbt. We can write kbt and 3. That's what we get. So this is expectation value of mu. Okay, so now you divide this magnetic moment by h. You will get here susceptibility. So susceptibility will be actually expectation value of mu by h. So that is mu and divide by, sorry, mu square, h will cancel out, divide by 3 kbt. That's the answer. Okay, so this is also a very well known question. Its derivation is given in all books which discuss theory of magnetic moment. Okay, in solid state physics as well as in statistical mechanics book, you can find this discussion. Okay, all right, so now let's move to, so this was not a new question, it was a theoretical question. So this is somewhat new question. It says angular position of a star is found to change by an amount of 0.2 arc second relative to very distant background star when measured by a telescope on Earth on 2 different nights separated by 6 months. Okay. Note that distance between Earth and Sun is known to be approximately 1. So that is the distance. Okay. So this distance, let's call capital R, between Sun and Earth. So let's see, this is Sun and Earth is revolving around it in circular orbit. Okay, this distance is capital R. Okay, now suppose in 6 months Earth goes from this position to this position. Now suppose there is a distant star. Okay, so there is a star here. Question says angular position of a star. So from here, if you see, and its angular position is this. Okay, now if you see from here, this is how light will be coming from a star. Okay, so we can see that from this position to this position, angle has changed by this fact, this one. Okay, so this is given to be 0.2 arc second. This angle is given to be 0.2 arc second. So from this position to this position, angle has changed by 0.2 arc second. Okay, so this distance is suppose r from here to here, and this is r and r, so this is 2r. So since this distance is very large, okay, this r is much greater than capital R, we are assuming. Okay, so therefore, because this angle is small, so obviously this this angle is very small, so that obviously this distance has to be very large. Okay, so therefore we can write this angle 0.2 arc second is equal to 2r divided by capital R by a small r. This is just like arc upon radius. Okay, so 2 and 2 will cancel out, so this is 0.1, and arc second को अगर degree में change करेंगे तो this you will have to divide by 3600. Okay, so that is degree. So let us change degree into radian. So this is pi by 180. Okay, so now we have written in radian. Okay, that will be equal to r by r. Okay, so therefore we are getting small r is equal to capital R, which is distance between Sun and Earth. Okay, so here this is capital R and multiplied by 3600 into 180. Okay, and divided by pi. That's what we get. So this is a somewhat calculative question. So distance of this star from Earth is actually this much. Okay, now question says if energy flux from a star is this, energy flux is this energy per unit time per unit area. So what is the approximate value of luminosity? Okay, so we have to find approximate value of luminosity. so which is given to be arc per second. That means we have to this luminosity जो दिया गया है यहाँ पे, that is actually power. Okay, we have to find power emitted by this star. Okay, see whatever power this star emits, okay, this is star, that power will spread in all directions. So when it is falling on earth, okay, it has already spread into a wavefront of area 4 pi r square. See, it will emit power in all direction. Okay, it is something like this. See, this is star and it is emitting power in all direction. So whatever power it has emitted, that has spread into this area. Okay, this radius is suppose r. So when it is falling, so its power emitted per unit area is given. Okay, energy flux. So if you want to calculate power, you will have to multiply F with 4 pi r square. Okay, when it is falling on earth. Okay, so this F is given to be 10 to the power minus 7 and 4 pi, and R we have calculated this one. Okay, so capital R will put from here 1.5 into 10 to the power 13 and multiplied by this. This is 36 into 18. This is 36 into 18 and 10 to the power we have 3. Okay, it's whole square and divide by pi also. Okay, so that's what we get. Okay, so that is the power. So we can calculate this. Okay, here is it giving correct order? Let's see. Yeah, so we can just approximate whether we are getting correct order or not. 10 power minus 7, and here we have 4 pi, and this is 1.5 into 10 to the power. We already have 16 power here, so we can put a dot. We can decimal here, and we can put a decimal here. So power will increase by 2. So we have 16 and plus 2, 18. So 18, and here we get 3.6 and 1.8 whole square. Okay, and now divide by pi. We have something like this, 0.2 arc second. So we 3600, and oh sorry, there was 0.1 also here. Okay, we forgot to write this one. Okay, that's why we are getting incorrect answer. So 0.1, so it will become 1800 actually. Okay, so this will be 1800. If we write here 1800, so it was 1800, so therefore one more 10 is there. Okay, one more 10. Actually, see here 0.1. So if you write it as 1 by 10, so that will multiply with this. So we get 1800. Okay, so one more 10 is there. So here we'll get um, one more 10. Okay, so let's write here one more 10. So basically 10 to the power we have 19. Okay, so now you see here we are getting 10 to the power 19 and it is a square. So we'll get here 10 to the power 38. So when you subtract this, you are already getting 10 power 31. Okay, so we are getting 10 power 31, but here we have other factors also. See, there is 1.8, 3.6. So at least these three will cancel out. So you will get here, and there is factor of 4 pi also. Okay, so when you do all this calculation appropriately, you will get something. I have done this calculation 1.2 into 10 to power 33. Okay, that's what you will get actually. So correct option will be this one. Okay, is the correct option, option A. So you can do this calculation. I have just told you how to do it. Okay, so basically angle was given. So using this angle, we calculated distance between the given star and the earth. Okay, and when it is emitting flux of energy, that is spreading into a wavefront of area 4 pi r square. So with that area we have to multiply. Okay, to get power. Okay, because this was energy per unit area per unit time, and here we have to calculate energy per unit area. All right, so that's what we are getting. Okay, all right. Now let's see this question. It says the binding energy EB of nucleide XZA with atomic number Z and mass number. This is given by, this is the binding energy semi empirical mass formula, where the constant parameters and all the constant parameter, these terms are given here. Now question says, for a neutron star consisting of only neutrons having uniform nuclear density throughout its volume, the Coulomb term is replaced by gravitational energy. Okay, so now we have to replace Coulomb term by gravitational energy. So therefore binding energy formula will be something like this: AV into A minus AS A to the power 2 by 3, okay, minus this term, Coulomb term is giving negative term, but if you replace it by gravitation, it will be 3g m square or divided by 5r. Okay, it is something like this. This is a gravitational term. And plus we have here A. Actually, it should be minus. Okay, they have incorrectly written here. Generally this term is negative. So here we'll write minus A. And since there is only neutron, there is no proton, so Z will be 0. Okay, so in that case, you will get capital A here. Okay, so this asymmetric term is actually, this actually comes with negative sign. Okay, so we have to write negative. Okay, so now here you see this AV is given to be 15.56 and AA is 23. So when you subtract these two, this will get a negative term here. So we'll write like this: minus of AA minus AV and A minus AS A to the power 2 by 3 and plus this term. See, mass M we can write as A into mass of proton. We can write like this because there are mass number is A and mass of proton and neutron are approximately same. So we can write total mass is equal to A times mass of proton, and radius is actually R naught A to the power 1 by 3. Okay, because here it says density is uniform, so we have to take radius of this form. Okay, because in nucleus also we know that density is uniform. In that case we get the radius dependence of radius on A to be of this form. Okay, so because of this statement, it says uniform nuclear density, okay, throughout its volume. So that's why we can take R equal to R naught A to the power 1 by 3. All right, now you see when you put all these things here, we get here A to the power 2, and here we get A to the power 1 by 3. So 2 minus 1 by 3 will get, so that becomes 5 by 3 actually. So we'll get here this is 0.6 and G, and here we get this mass of proton square and A to the power 5 by 3 and divided by this R naught will come here. Okay, so this is the gravitational term. So basically we'll focus on this. Power of A is 5 by 3 here. Okay, here power of A is minus 2 by 3 and here power of A is, so sorry, 2 by 3 and here power of A is A. Now if you plot this, okay, if you plot it, you will get something like, see, these two are negative terms, okay, and this is positive. So when A is small, these terms will dominate, but when A is larger, this term will dominate. So if you plot it, you will get something, a graph of this type. Okay, you will get something like this. This is binding energy and this is A. So graph is will come out to be something like, you can use a Desmos to plot it. See, it is something like this. So here you see binding energy is negative, okay, and this side binding energy is positive. So this is the value of A for which minimum value of A minimum, for which binding energy is becoming positive. Okay, so all right. So therefore, stability will come only after binding energy becomes positive. So from here onwards, binding energy is positive. So this is the minimum value of A for neutron star to be stable. Okay. So therefore, at this point, you see binding energy is 0. And after that, so to obtain the minimum value of A, we will put binding energy to be equal to 0. After that, binding energy is positive. So higher and higher value of A will be possible. Lower value of A will not be possible here, because for lower value of A, we are getting negative binding energy. Okay. All right. So therefore, we are getting here EB. When we put EB equal to 0, we'll get here something minus AA minus AV and multiplied by A, and minus AS A to the power 2 by 3 minus 0.6 G MP square a to the power 5 by 3 and divided by r naught. Okay, this we are getting. See, to make calculation simple, okay, what we do is let us neglect. See, this term is this has the least power of a. This is less than 1 power. Okay, so we are neglecting this term. Okay, to make calculation simple, neglect it. If you neglect it, okay, this term is positive actually. This term is positive. Okay, so when you neglect it, then from here you will get value of a. You will get here a to the power. See, 5 by 3 minus 1, so you will get 2 by 3. Okay, so a to the power 2 by 3 will be equal to this a minus ab, and here r naught. Sorry, this is r naught, and divided by 0.6 g and mp square. G and mp square. This is what we are getting. Okay, and so therefore this is a minimum actually. A minimum will be equal to a minimum will be just a minus av, and here r naught divided by 0.6 g and mp square. Okay, whole power 3 by 2. This we are getting. Okay, so we can put all the values that we have. Okay, and from here we will get a minimum. So I'm not doing this calculation. I have just given you hint. Okay. So if you put everything is given here. So you put all the things. We know G, we know mass of proton. Okay. Everything. So from here, if you calculate, you will get a minimum to be of the order of 10 to the power 55. So this is a huge number actually. Okay. It comes out to be of the order of 10 power 55. Okay. Now, so we have gotten a. Now we'll put back a in this relation. Okay, so here we r naught, we know that r naught is of the order of this is 10 to of the order of 10 power minus 15, 1 point something 1.2 into 10 power minus 15, and here you get 10 power 55 and power 1 by 3. Okay, so now you just do this calculation. Okay, so when you do this calculation, you will get option A here. Okay, this answer is coming in meter, so that you will convert into kilometer. Okay, so you will get option A. So that is the method here. Okay, you replace this term with gravitation term, and if you look at the plot, you get something like this. So minimum value of A for which binding energy is becoming positive is this one actually. At this point, binding energy is 0, so we'll put binding energy 0 to obtain for minimum value of A. Okay, and from there we are getting the radius. Okay, so that is the minimum. See, we are using minimum value of A. Okay, here we are using minimum value of A, so that will be the minimum smallest radius of neutron star. Okay, there will be higher values of A also possible. Okay, now see, this is the last question from part C. It says here, because of electron and positron collision, some kaon is produced. Okay, and that decays into pion, pi plus and pi minus. Okay, now you see these are two pions. Now see, to conserve momentum, we know that two pions, suppose there are two particles being emitted, so they actually travel in opposite direction. Okay, they travel in opposite direction. Now if this is positively charged particle and this is negatively charged particle, okay, so they should travel in opposite direction, right, to conserve momentum. All right, now suppose there is magnetic field here. Suppose b is there. Okay, so if you calculate because of magnetic field, this will deviate. So this is v, and v cross b, if you calculate on the force on this positively charged particle, it will be in this direction, so it will deviate like this. Okay, now if you calculate force on this v cross b, force on this will be in this direction, so it will deviate like this, right? V is in this direction, b is in this, v cross b. Force, since it is negative, so it will deviate like this. Okay, I think something is there. So these are the options given. See, so actually what is happening, I think, is from this position, you see, actually from figure, it looks as if, see, if I draw tangent to the path, okay, here, so it looks as if they are going in same direction, okay. Here also it looks as if almost they are going in same direction from tangent, okay. So if we assume that they are going in same direction, that can happen only if chi1 already has some momentum, okay. So if they are going almost in same direction, then in that case, see, if there is positively charged particle, see, actually the trajectory is going this way and this way. Trajectory of one is not going up and trajectory of the other is not going down. Okay, so we'll have to assume that both pi plus and pi minus are actually traveling in same direction. Okay, so that can happen if this k particle, k on, okay, k meson has already some momentum. Okay, so if it already has some momentum, okay, then this can happen. Okay, so let's say that there are two positive particle and negative particle. They are going in same direction. Okay, so what will happen if there is suppose upward magnetic field? So force on this, if you calculate force on this, velocity is in this direction, magnetic field is in this direction. So force on this is in this direction. So positively charged particle will deviate like this. Okay, and if you calculate force on negatively charged particle, it will be in opposite direction. So negatively charged particle will deviate like this. Okay, so it is something like this. Okay, so this way, see, if velocity is in this direction, magnetic field is in this direction. So this is minus pi minus, this will be path of negatively charged particle, pi minus, and this will be path of positively charged particle. But this kind of path we can get only if initially they are moving in same direction. But if they are moving in opposite direction, we will get this kind of path. Okay, so here from figure, actually it looks as if they are all in same direction. See here, but this path is not appropriate, okay, because if they are going in opposite direction, okay, opposite direction, we should be getting this kind of path. Okay, so this D option is not appropriate because it shows opposite path. Okay, one is going this way, the other is going this way, but they are not deviating in same direction. In opposite, when path is their velocity is opposite, they are deviating in same direction. You see, this one is deviating leftward and this one is also deviating leftward, so that is not given in this option. Okay, so therefore you'll have to assume that initially they are going in same direction. Okay, because of some initial momentum of this k meson. Okay, so if they are going in same direction, one will deviate this way and the other will deviate this way. Okay, so therefore the most appropriate option should be B option. All right, so we have completed this C part. Now let us discuss other parts. So we are moving to part A now. Okay, so these are actually easy questions. Let's see. There is a surface given. So this is the function that we have. Okay, now question: which of the following is vector normal to it at this point? Okay, so normal, we know that is calculated. Normal vector is calculated using gradient of the function. If you want to calculate unit vector, then you will have to divide by its magnitude. So if you calculate gradient, you have del f by del x I cap and del f by del y and j cap and plus del f by del z and k cap. This is what we have. So let's differentiate it with respect to x. When you differentiate it with respect to x, you get here 2x. So it becomes 8xy. And when you differentiate this one, you get minus 2 y square and I cap. Plus, when you differentiate it with respect to y, you get here 4y square. Y gets differentiated. And from here, you get minus 4xy and j cap. And when you differentiate with respect to z, you get here 9z square and k cap. Okay. Now let's put the values. Okay. So see, the values are 2, 3, 1. Okay. So in place of x, you put 2 and 3. So this becomes uh, 2 multiplied by 3, 6, and multiplied by 8, you get 48. Minus here, when you put 3, it becomes 9 and to 18. You get here 18 I cap. Plus here you get 9. So this becomes 36 minus, and here 2 and 3 you put. So you get 2 multiplied by 3, 6, and multiplied by 4, 24 j cap. Plus here you put 1. So you get 9 k cap. Okay. So subtract these two, you get minus 30 I cap and plus Here you get 12 j cap and plus 9 k cap. That's what we are getting. Sorry, plus 30. It was plus 30 I cap and plus, I made a mistake, I think. Let's see. When we differentiated, oh, sorry, I wrote here y square. It was not y square, but actually it was x square. So it is 4x square actually. All right. And when you take it, so here it is 4x square. So when you put here 2, so it becomes actually 16. Okay, so when you put here, you get 16. So you get here minus 8. This is minus 8. Minus 8 j cap. Okay. And plus 9 k cap. So this is quite a straightforward question. Okay. Although we can make some calculation mistake. So correct option is this one. Okay. Now let's move to some other question. See this question here we have to calculate its derivative f prime x. Okay, we have to find f prime x. So when you differentiate this function, you get 2 by root 3, and here e to power minus root 3 and x square and mod x. See, derivative of exponential gives you exponential. Okay, but now you will have to differentiate this inside term. So when you differentiate this term, you get here minus 2 root 3 and x and mod x. And then you differentiate this term. So you get here minus root 3 x square and d mod x by x. Okay, this you are getting, and we are evaluating this at x equal to 0. So when you put x equal to 0 here and here, you get 0 actually. So this f primed at x equal to 0 is 0 actually. X equal to 0 is 0. Okay, so therefore correct option is A. Okay. All right, now this question, it says consider symmetric matrix and orthogonal matrix O, which can diagonalize this matrix by an orthogonal transformation is given by. See the matrix which diagonalizes this given matrix is actually obtained by eigenvalues, sorry, eigenvectors of this matrix. Okay, मतलब अगर ये matrix M, ये जो matrix O है, if it diagonalizes this matrix, then its column vectors are actually eigenvectors of this matrix. Okay, तो हम लोग चेक कर सकते हैं, ठीक है, कि जो कॉलम, ये जो कॉलम है इसके, मतलब कॉलम वेक्टर, these column vectors, these column vector must be eigenvector of this matrix. Okay, so let us check that. So here we can take 1 by 3 common, so we'll get 1 0 and 2 and 0 1 and 0, and here you get 2 0 and 1. And now here, this column, if you take this column 1 by root 2, I'll take common from here. So you get 1, 0, and 1 actually. Okay, here. So let us multiply and see what we are getting. So if you multiply it, you get here 3. This column multiplies with this row. And here, when you multiply, you get 0. And here, when you multiply, you get 3. Okay, so you get 3 and 1, 0, 1. So we can say that this column, I have taken root 2 common, so 1 by root 2 I have not written here. So that's why we are getting 1, 0, 1. So, and here 1 by 3 I have taken common. Okay, so we can say that this column is an eigenvalue of this matrix with eigenvector of this matrix with eigenvalue this. Okay, similarly this one, see 1 0 2, this matrix is, I have taken 1 by 3 common, so 0 1 and 0 and 2 0 and 1. Now second column we are checking 0 1 and 0. So when you multiply this, okay, first term we get 0, this column multiplies with this, and second you get 1, and third one when you multiply you get 0. So we can say that this is also an eigenvector with eigenvalue 1. Okay, now let's check third one, 1 0 2 0 1 and 0 and 2 0 and 1, and third one we are checking this one, this column. So 1 by root 2 I'll take common, so this is 1 0 and minus 1 we have. Okay, so when you multiply, you get here, just do the multiplication, you get here minus 1, right? It multiplies 1, and from here you get minus 2. So minus 1, and here you get 0. And when you multiply this, okay, you get 1 here. So you can take minus 1 common. Okay, you will get here 1 0 and minus 1. So again, you see when you multiply, when this matrix acts on this column vector, you are getting same column vector. Okay, here also the same thing is happening. You are getting same column vector with a multiplication factor of 3. So therefore 3 is eigenvalue, here 1 is eigenvalue, and here -1 is eigenvalue. So all these column matrices, column of this matrices are actually eigenvector of this eigenvector of this matrix. So therefore this matrix will definitely diagonalize this matrix. Okay, so therefore option A is correct. Okay, you can check in other option. You will find that these column are not actually eigenvector of this matrix. Okay, all column are not eigenvector of this matrix, so therefore these matrices cannot diagonalize the given matrix M. Okay, so therefore option A is correct. Now this question, see, it says a ball is sliding from here and then it falls like this. Okay. So question says the same experiment is repeated on moon, then what the value of this D will be. Okay, D becomes D prime, so how D primed is related. So what will happen, see, it has fallen from here. You can write here potential, see this, I'll take potential energy 0 level, so here potential energy is mg h1, and that converts into kinetic energy. Here it becomes half m V square here. So from conservation of energy, this kinetic energy must be equal to this potential energy. So we'll write it like this, mm cancel out. So from here you get V is equal to 2g h1. Okay, so here from here it falls straight actually. So horizontally it starts. So initial vertical velocity is 0 here. So now it is falling a vertical distance of h2 under gravity. It is freely falling, so its acceleration will be equal to g. So now we'll apply this formula for vertical motion from here to here. Actually, vertical motion is equal to ut plus half at square. Okay, so this will write h2, initial velocity is 0 plus half, and here this is g and t square. So if you calculate t, you get here 2h2 by g. Okay, so that is the time. Now if you calculate horizontal distance, so for horizontal motion, if you write this s equal to ut plus half at square, then s is, we are writing d, that is u is initially this much, root under 2g h1, and time of fall is 2h2 by this time of fall we have calculated here, h2, and horizontal acceleration is actually 0 when object is falling under gravity. So this term is 0. So g will cancel out. So you get here basically 4 times h1 into h2. You get d. So this is independent of g actually. So on moon g becomes g by 6, but here it is independent of g. So therefore on moon also we'll get the same answer. So therefore correct option will be A. Okay, since it is independent of g. Okay, now this is a question from SHM. It says particle executing simple harmonic motion. Okay, so this is we have to find time period of oscillation in terms of position and velocity. So there is a formula actually, omega root under a square minus x square. Okay, so here if you write v1, we'll write here omega root under a square minus x1 square. So, and similarly, so v1 square will be equal to omega square, and here a square minus x1 square. Similarly, you can write v2 square equal to omega square, and here a square minus x2 square. Okay, so subtract the two. Okay, so when you subtract the two, you get here v1 square minus v2 square is equal to omega square, and here you get x2 square minus x1 square. So therefore, omega is equal to root under, we are getting v1 square minus v2 square, and divided by x2 square minus x1 square. Okay, so this is 2 pi by t is equal to root under v1 square minus v2 square, and divide by x2 square minus x1 square. Now from here we can calculate t. So if you calculate t, you will get here 2 pi and root under x2 square minus x1 square, or divided by v1 square minus v2 square. Okay, so therefore we are getting, see here x2 square, v1 square minus v2 square. So which is correct? Option A is correct. Okay. Now here it's a solid cylinder of uniform density rolls down fixed inclined plane. So we have to get a fraction of total kinetic energy of a cylinder associated with its rotational motion. So if you calculate rotational kinetic energy, see, this is equal to half I omega square actually. So this becomes half, and I for cylinder is mr square by 2 and omega square. That is the rotational kinetic energy. If you calculate total kinetic energy, it is rotational kinetic energy plus translational kinetic energy half mv square. Rotational kinetic energy, here we have m r square omega square by 4 plus half m p is omega square और r square, ये इतना आ गया. So p by 4 m r square और omega square, that's the total kinetic energy. ठीक है, तो this is total kinetic energy. So let us divide the two fraction. We have to calculate rotational kinetic energy divided by total kinetic energy. So if you calculate the two, see, factor of 1 by 4 will cancel out from here. M r square omega square will cancel out, and you will get a factor of 1 by 3 here. Okay, this 3 will remain. So therefore, correct option is this one. Now this question, it says, this is Young's double slit experiment. Okay, so consider an electron double slit experiment as shown in figure. So while slit S1, if now within the shaded region marked C, constant magnetic field is applied, field pointing outside is turned on, the fringe pattern. See, question here is, suppose electrons are passing through the slit and we are getting a interference pattern here. Okay, there was no magnetic field here. Now we are applying magnetic field here. Okay, so magnetic field is only within this region. So question is how the interference pattern will change. See, the situation is something like this. There is situation like this. There is slit, and there is a small region where we are applying magnetic field. There is no magnetic field outside this region. So now from here, this is electron gun. Okay, so electrons are passing through this and this. So it appears as if electrons are not interacting with this magnetic field. So nothing will happen. Okay, so that's why a question says no change is not given actually in option. So what will actually happen, see, if you are applying a magnetic field here, okay, vector potential will be in this direction like this. Okay, so these circles are actually vector potential. Okay, these circles are vector potential. Suppose their direction is like this. Okay, so electrons which are going in this direction, okay, they face a vector potential which is opposite to their direction of motion, and here a vector potential will be in this direction. So electron going in this path face a vector potential which are in almost same direction, or so here vector potential is in same direction as the direction of the momentum of the electrons, or we can say here angle between vector potential and momentum is acute angle, and here it is obtuse angle, because vector potential is in this direction. So here vector potential is in this direction, sorry, in this direction like this, and momentum is in this direction. Okay, this is the direction of vector potential. Here vector potential is somewhat like this and momentum is like this. Okay, this is vector, oh, sorry, ulta ho gaya. Here momentum is like this and vector potential is also in this direction. Okay, so here angle will be acute angle, here angle will be obtuse angle. Okay, actually, so the two electrons face a different situation, so because of that they will there will be a phase difference between the two electron beams. Okay, इस electron beam में और इस electron beam में एक phase difference होगा. Actually what happens, when electron passes through electromagnetic field, you write Lagrangian like this, half mv square. Okay, and we have minus q phi, where phi is electrostatic potential, plus q a dot v. Okay, this is the Lagrangian. Okay, so you see in Lagrangian we have a term a dot v, where v is velocity of particle and a is vector potential. Okay, so because of this term, okay, here you get this term will be negative in this region and it will be positive in this region. So because of the presence of this term, if you write Hamiltonian will be something like this: p minus q into a whole square, or divided by 2m plus q phi. So again, for these electron, you will get, since p and a are opposite, okay, so you will get some positive kind of term here, and for these electron you will get negative term. Okay, so obviously there is difference in Hamiltonian and Lagrangian. Okay, so similarly there will be difference in quantum mechanical Hamiltonian also. Okay, and because of which there will be a change in phase. Okay, there will be change in phase. Okay, and if there is change in phase, we know that interference pattern shifts. Okay, this situation is somewhat similar to the situation in which we put a glass plate in front of one of the slits. Okay, so we know that when we put glass plate, suppose we put a glass plate in front of one of the slits, then interference pattern shifts. Okay, so this similar, something similar is happening here. Okay, there is a quantum mechanical phenomena related to this, which is called Aharonov Bohm effect. Okay, I this is, so this is somewhat related to that phenomena actually. Okay, so because of the presence of vector, so main explanation of this is something like this: because of the presence of vector potential. So because of the presence of vector potential, there is phase change in wave function of electrons of the two beam. Okay, and because of that phase change, actually there will be a shift in wave interference pattern. All right, now let's move to another question. See, the question says an atom at rest emits and absorbs photon of frequency nu and recoils with momentum p. The frequency of internal transition of electronic level is nu naught without accounting for recoil. So if there is no recoil, then internal transition has frequency this much. Assuming a process is non-relativistic, the fractional difference between photon frequency for emission and absorption respectively are. Okay, so that's what we have to calculate, fractional difference. So for emission and for absorption. So let us do one by one. So let us first do emission. See, because of internal transition, it is emitting a photon of frequency nu naught. So h nu naught energy जो emit हो रहा है, okay, that will get converted into energy of photon h nu and some kinetic energy of atom. Actually, what happens? See, suppose this is the atom, and this atom, because of internal transition between some higher and lower level, we get energy h nu naught. Okay, that's what question says. Internal transition में frequency जो obtain हो रहा है, that is nu naught, so energy will be h nu naught. Okay, now when this photon comes out, okay, because of the recoiling of atom recoils in opposite direction, its energy of photon becomes h nu. Okay, so therefore, see, its energy is this much, so momentum will be h nu by c for photon. So to conserve momentum, this momentum must be equal to h nu by c. So these two are actually equal. Okay, now this energy h nu is getting converted into these two energy: kinetic energy of atom, its mass is m, and energy of photon. So therefore here we have h nu naught in emission process is must be greater than h nu. Okay, so therefore when we are calculating this term, nu minus nu naught or divided by nu. Okay, so this is basically, we can write it as like this: h nu minus h nu naught and divide by h nu. So obviously this term is actually bigger, so we are getting this negative term. Okay, so now this energy is converting into this these two part. Okay, h nu naught is becoming h nu and kinetic energy of atom. So basically difference of these two energy will be equal to kinetic energy. So this difference, so it is clear that this is negative because this is higher. So this difference will be kinetic energy, okay, or divided by h nu. Now this is minus kinetic energy is written like this for non-relativistic case. It says it is non-relativistic, so we'll write kinetic energy as p square by 2m upon h nu. Okay. Now p, as I said, this p is actually equal to h nu because to conserve momentum, energy of photon, this is suppose photon. Okay, so momentum of photon must be equal to momentum of recoiling atom. Okay, so momentum of photon is this much, so we'll write this here h nu and divided by c whole square and divided by, we have 2m and h nu. So one h nu will cancel out and there is negative sign. See, this term is smaller, this term is bigger, so that's why this is negative of kinetic energy. Okay, so finally we are getting here one h nu will cancel out, so we'll get h nu and divide by 2m into c square with negative sign. So in case of emission we have this. So you can see here emission is written, and here we have h nu divided by 2mc square. Okay, here in emission we have positive, and in emission here we have nu naught. Nu naught is there, but nu naught won't be there. Nu will be there only. Okay, so therefore this is the correct answer. Okay, first option. See, we can write for absorption also. See, for if we write for absorption, this is the situation. This is the atom at rest, and suppose a photon is coming, its energy is h nu. Now, this photon will cause some internal transition in the atom. Okay, so we'll have this kind of situation. After this, we'll have atom in excited state. This is atom, suppose in excited state, and it is moving. Okay, so it is moving with momentum p. So again, to conserve momentum, momentum of this atom must be equal to momentum of incident photon, which is equal to h nu by c. Okay, so that is the situation, and it there is internal transition, okay, in the atom, because of which because it has absorbed the photon, so it can absorb the photon only if there is internal transition. So because so for internal transition it has absorbed energy h nu. Okay, so basically h nu gets divided into two part, h nu naught and kinetic energy of atom. Okay, because it absorbs energy h nu naught from h nu to go to high excited state. Okay, and also it gains some kinetic energy, because of which atom starts moving. So if atom is moving, then to conserve momentum, this momentum must be equal to this much. Okay, so this momentum and this momentum are equal. Okay, so now again this is dividing into two parts, internal energy and kinetic energy, so therefore difference of the two must be equal to, so we have h nu minus, so we have to calculate here this one, nu minus nu naught and divide by nu. So we can multiply h by h, we'll get here h nu minus h nu naught and divided by h nu. So here this difference is actually equal to kinetic energy, and here remember this h nu is actually greater than h nu naught, because h nu is getting divided into two parts now here. Okay, so this is kinetic energy and divided by h nu. Yes, kinetic energy is actually equal to, as I said, p square by 2m and divided by h nu. And as I said, to conserve momentum, this momentum of atom must be equal to this h nu by c. So we'll write here h nu by c whole square and divide by 2m. See, we are writing kinetic energy as p square by 2m because it is a non-relativistic situation. And divide by h nu we have. So h nu will cancel out. So we'll get h nu upon 2m into c square. See, this is positive. Okay, because this term is greater, so this is positive term. Okay, which is given here. In absorption, we have h nu divided by 2mc square. Okay. So this was a question from based on conservation of momentum actually. Okay, and we can say it is related to conservation of energy also, because here we are saying that kinetic energy is equal to difference of these two energy. Okay, but ignoring relativistic phenomena. Okay, because we are using kinetic energy as p square by 2m, which is non-relativistic formula for kinetic energy. Okay. Now this question, it is related to quantum mechanics. It says consider an atom in consider an electron with mass e and charge minus e and spin half, whose spin angular momentum is given to be this. It is in magnetic field. Okay, so if you write its energy, see here. See, if you write Hamiltonian, oh sorry, it will be something like this. Magnetic moment dot magnetic field. So this can be written as magnetic moment, see some Landesi factor, 4 magneton, okay, and s dot b here, okay, and they will be divided by h bar. So that is the energy. Okay, so that is the Hamiltonian. Okay, now see, magnetic field is in some arbitrary direction. Okay, so if you calculate, this is Hamiltonian operator. Okay, so if you calculate its eigenstates, we can use Pauli matrices, okay, to calculate its eigenstates easily. So if you calculate eigenstates, suppose you get state 1 and state 2. So one state will be will represent state parallel to magnetic field and the other opposite to magnetic field. Okay, with corresponding eigenvalue, you will get h bar by 2 and minus h bar by 2. Its eigenvalues will be h bar by 2 and minus h bar by 2. H or something multiplied by these terms. Okay, this will be, these are angular momentum states actually, corresponding angular momentum states. Okay, so all right. So suppose these are two eigenstates of Hamiltonian with corresponding angular momentum state h bar by 2 and minus h bar by 2. All right. So now question says at time t equal to 0, electron is at rest in Sz equal to plus h bar by 2 state. Okay. So this for this state, see Sz is equal to plus h bar by 2 state. We have we represent this state by 1 0. Okay. So this 1 0 can be written as, see, this 1 0 can be in, this is initial state. We can write it as ket 0. Okay. So this is initial state. This can be written as some C1 and ket 1 plus C2 and ket 2. Okay. C1 ket 1 and C2 ket 2. Okay. So here, if you calculate C1 modulus, it comes out to be actually cos theta by 2. And so this is a detailed theory. If you calculate C2 modulus, it comes out to be sin theta by 2. Okay. So if theta 1 and theta 2 are, if theta is not equal to 90 degree, the magnetic field is not making, see, it is something like this. This is Z direction. Magnetic field is something like this. And this angle is theta. Okay. So if theta is not equal, then C1 modulus is not equal to C2 modulus. ये दोनों का modulus equal नहीं होगा. Because if theta is 90, then you will get here 40 cos 45 and sin 45, which will be equal. Okay. So since these two are not equal, okay, these two are not equal. So therefore, at any later instant of time, if you write psi like this, C1 ket 1 and e to the minus iota E1t and divide by h bar and plus C2 ket 2 and here e to the minus iota E2t divided by h bar. If you write this, okay, at any later instant of time, if modulus of these two are not equal, okay, this wave function can never be orthogonal to this. Okay, because if you assume that it is orthogonal, okay, what you are going to get here is this. See, if you assume these to be orthogonal, then it will lead to a mathematical contradiction. Okay, you will not be able to, you will get some mathematical contradiction. Okay, on right side you will be getting 1 and on left side you will be getting not equal to 1. Okay, so you can check that if you want. Okay, you can just uh, apply condition of orthogonality of these two. So you, if you do that, you will get something like this: C1 modulus square. See, in the beginning itself we are assuming C1 is not equal to C2, so you will get here this here you will get it from iota E1t divided by h bar plus C2 modulus. If you multiply these two, okay, orthogonality condition, if you apply, you will get it per iota E2t and divide by h bar, that is equal to 0. Okay. So their inner product we have made 0, psi 0 and psi t. Their inner product equal to 0 we have taken. All right. This is what we are getting actually. Okay. Now, you see, we are writing C1 modulus square by C2 modulus square is equal to minus e to the power iota E2 minus E1 into t divided by h bar. Is that okay? So now if you calculate modulus, let's take its modulus. So you know that modulus of exponential is 1. Okay. So here we will get C1 modulus square will be equal to C2 modulus square. Okay. So if we impose orthogonality condition, we will end up getting C1 modulus square equal to C2 modulus square. But from the beginning, we had assumed that C1 modulus square is not equal to C2 modulus square. So therefore, if these two are not equal, the wave function can never be orthogonal, because if they become orthogonal, these modulus of the moduli of these two must be equal actually. Okay. So in the beginning itself, we are assuming these are not equal. Okay, because in general they may not be equal, and if they are not equal, the later on wave function can never be orthogonal. Okay, because for orthogonality, modulus of these two has to be same actually. Okay. So therefore, its correct answer will be it will never be orthogonal, because it is a general situation. So in general situation, actually, see, this is the Hamiltonian. Okay, if you calculate its eigenstates, you will get this. But initial state is this. Okay, so this initial state can be written as linear combination of these two eigenstates, and So coefficient that you are using here, if their moduli of these two coefficients are equal, okay, then only at later instant of time this wave function can become orthogonal to later on wave function can become orthogonal to initial wave function. Okay, but if modulus are not equal, then that will never happen. Okay, so that's why in the beginning we have to assume in a general situation that these two are not equal. Okay, so if these two are not equal, later on wave function is not going to become orthogonal to initial state. Okay, so therefore infinite, it will never become orthogonal. Okay, so that is the correct answer. So I have shown that here. Okay, see, I assumed initially these two are not equal, but if we are imposing the condition of orthogonality, we are getting the two to be equal here. Okay, so that contradicts with initial assumption. Okay, that's why we'll say that it will never become orthogonal. Okay, it will never become orthogonal. All right. Now this one. So this is a very elementary question. It says an electric field due to a uniformly polarized dielectric sphere. So this is uniformly polarized dielectric sphere. So this side will be negatively charged. This side will be positively charged. Okay. So here inside electric field will be from positive to negative like this. Okay. And outside from positive to negative like this. Okay. Something like this. So from positive charge, field line will start and they will terminate on negative charges. Okay. So something like this. Okay. So that is the situation. So this kind of field you see is given in option A. Okay, field lines are downward inside and outside is starting from positive charge to negative. Okay, so this option is correct. Okay, this is a very well known top concept that is discussed in most of the books of electrodynamics. You can see this is given in Griffith also. Here we say that it is uniformly polarized, so field inside is actually equal to minus P upon 3 epsilon naught, and field outside, this is uniform actually. This field is uniform. So here field lines are straight actually inside, and since E inside is opposite to P, so therefore P is upward, so field line has to be downward. So you see here field line is given to be downward only in option A. Okay, so if we know this formula, it's then this from this formula itself we are getting option A, because inside inside a uniformly polarized sphere, field is minus P upon 3 epsilon naught, and from here we are getting field line must be straight because it is uniform, and it must be opposite to polarization, and that is given only in option A. So therefore option A has to be correct. And field outside, in such situation is, if you calculate field outside, it is exactly same as field of dipole. Okay, it will be exactly same as field of dipole. So if somebody knows only this formula, then also the option can be inferred. Okay, all right. Now here, this is also an elementary question on polarization. See, it says radiation is going like this. See here, this is a wire grid. So this is wire grid. Okay, so when radiation passes through it, okay, this all the component of electric field which are parallel to the wire. Okay, suppose the electric field is in this direction, so it will have a component parallel to the wire and perpendicular to wire. So parallel component actually accelerates electrons. Okay, so therefore that parallel component gets absorbed. Okay, but perpendicular component of electric field which is in this direction is not able to move the electron. Okay, so because electron don't have enough space to move in this direction, so electron do not get accelerated in this direction. Okay, so that's why this component cannot accelerate electrons, so this component doesn't get absorbed. Okay, so therefore after passing through, suppose this is the radiation, so after passing through it, radiation will have electric field in this direction, because this electric field is not absorbed by these wires, because this electric field is not able to accelerate the electrons, okay, inside the wire. Okay, so that's why this direction is z direction. So we'll say that transmitted wave will be polarized along z direction. See, this will be the direction of electric field, so we'll say since electric field is in z direction, so we'll say that it is polarized in z direction. Okay, now see, this question is related to rotation of this is related to electromagnetic induction. See, this can be done using flux method. Okay, or we can simply see here what is happening. This loop is being rotated in magnetic field. इसको कैसे rotate placed? I think it is rotated clockwise, है ना? Sorry, anti-clockwise. the loop is then rotated counterclockwise. ठीक है, यहाँ पे लिखा हुआ है counterclockwise. So it is rotated counter like this. Okay. So for some time it will remain inside the magnetic field. Okay, until this portion. This OQ line rotates by pi by 2. Till that time it will be inside the magnetic field. So there is no change in flux. So therefore there won't be any EMF. Okay, कोई EMF इसमें induce नहीं होगा. Okay, so therefore for some time EMF will be 0. Okay, so that is shown here. So when it is coming out, okay, when it is coming out, flux will start decreasing. So if flux starts decreasing, then we will have to point our thumb in the direction of magnetic field. So in that case, current will be in this direction. Okay. So it says that this here some convention is given. If direction of PQOP, see PQOP is taken to be positive. Okay. So initially, what is happening when it is so this direction is being taken to be positive direction. Okay. Then correct graph for EMF generated in the loop is okay. So what is happening here? See, when it is coming out initially. Yeah, so when it is coming out, flux is decreasing. Flux is decreasing, so magnetic field is downward. Okay, magnetic field is downward actually here. It is into the page. So we'll have to put thumb in the direction of magnetic field. So when we put thumb in the direction of magnetic field, our finger is curling opposite to this arrow. So initially EMF will be negative actually. Okay, sorry, I had said upward. Okay, so actually this cross indicates that magnetic field is downward. So we put thumb downward to support the flux. Okay, because initially flux will decrease when this OQ line comes out of the magnetic field. So we'll put thumb downward to increase the magnetic flux. So in that case, current induced will flow in this direction, which is opposite to given arrow. So EMF will be taken to be negative. Okay, so there will be negative EMF. Okay. For some time, the loop will be outside completely the magnetic field. In that case, flux is not changing. Okay, flux is not changing, so there won't be any EMF. So again, there will, EMF will be 0 for some time, and when it is entering into it, then flux will be increasing. So to decrease the flux, we'll put thumb opposite to magnetic field. So in that case, current will be flowing in this direction. So this direction is being taken as positive. So we'll say that EMF will be positive. So situation is something like this. For some time, flux is 0 because this loop is completely inside the magnetic field. When it is coming out, then flux is negative, and when it is entering, so when it is completely outside, then again there is no change in flux. So in that case, EMF is 0, and when it is entering into the magnetic field region, in that case flux is increasing, and we are getting positive EMF because in that case direction of induced current is same as the direction given here. This direction is being taken as positive. Okay, so there is situation 0, then negative, then 0, again 0, and then there is positive EMF, and then again when it rotates inside the magnetic field, EMF will be positive. So that kind of situation is there. And if you want to calculate whether a magnitude of EMF varies with time or not, because see here in options, if you see this kind of graph is given, sorry, it is something like this. Here you see there is variation of EMF also. So if you want to calculate that, you can just draw this figure something like this. See, this is the region where there is magnetic field. Okay, and suppose at some instant of time, this line, this is O and Q is here. Okay, then perpendicular to this is P. This P is here, and this is semicircle. So it is something like this. So this portion has suppose come outside. This angle is suppose theta. Okay, so this portion will be inside. This angle is pi by 2 minus theta. Okay, so flux we can calculate. Flux is magnetic field into area. So this is magnetic field, and area will be actually 1 by 2 r is square, r is radius, and here pi by 2 minus theta. You can check area will be equal to this much. That is the area of the sector. Okay. All right. So this is the magnetic flux. We can write it as phi b. So EMF will be equal to minus d phi b by dt. When you differentiate it, d theta by dt will become omega. So EMF, value of EMF that you are going to get is 1 by 2 b r square and omega. You can see this EMF is actually constant. Okay, so that's why EMF won't be varying. Okay, there is no time dependence actually. Okay, There is no time dependent. D theta by dt becomes omega. So therefore, correct option will be this actually, because magnitude of EMF is remaining constant. It is only becoming positive and negative. Okay. Okay, here we have to, in this question, we have to calculate, you can read the question later on. See, we have to calculate change in entropy as gas goes from this side to this side. Okay, so we can write this as dq by t, and here we can write it as du plus pdv and by t, and here this du we can write as f by 2, sorry, some f by 2 u, you can write for ideal gas f by 2, and let's say r, and nr, n is number of moles, and dt, nrt will write, so it will become dt, and then there is t here also, okay, plus p by t and dv. So using ideal gas equation, we have pv is equal to nr t, okay, or we can write per particle, we have to calculate, so we can write pv is equal to nkbt. Okay, this we can write, so we have p by t is equal to nkb by t, sorry, nkb by v, p by t is equal to, so we p in place of this p by t, we can write nkb by v. Okay, so we have here n r into f by 2 and ln t2 by t1 plus here you will get nkb here, and dv by v integration will give you ln v2 by v1. Now question says v2 is equal to 2v1, okay, but t2 is equal to t1, so therefore this term will be 0. Okay, that is change in entropy. So change in entropy is equal to, this term is 0, and from here you get nkb ln 2. Okay, but entropy per particle we have to calculate, so delta S by n will be equal to kb ln 2. That's the answer. Okay, so first option is correct. Okay, now this question is also related to statistical mechanics. It says 5 bosons, identical bosons, are distributed in energy levels. Suppose there is energy level E1 and E2. So E1 has a degeneracy. It has degeneracy G1 is equal to 2, and E2 has degeneracy G2 is equal to 3. Okay, find the number of microstates if there are 3 bosons in E1. इसमें N1 is equal to 3 है और इसमें N2 is equal to 2 है. Okay, so degeneracy, there number of microstates is actually given by product of something like this: Ni plus Gi minus 1 mod factorial divided by Ni factorial, and here Gi minus 1 factorial. So that is the formula. Okay, so let's put, when we put this first level, so here n is 3 and g is 2, so 3 plus 2 minus 1, so this will become factorial 4, and divided by n is 3, so this is factorial 3, and g is 2, so this is factorial 1, multiplied by this multiplication. From here we 3 plus 2 4 minus 1, so again 3 plus 2 5 and minus 1, we get here 4, and here n is 2, so here we get factorial 2, and g is 3, so 3 minus 1, we get factorial 2 again, 3 minus 1 2. So from here we get, this is 24 into 24 and divide by 6 into 4, so this is 24 cancel out, so you get 24. Okay, so correct answer is this is the number of microstates. Now this is another question from statistical mechanics. Here we have to calculate, see, 2-level system is there. This has energy E and the other has energy 0. Okay, this is E1 and this is E2. Okay, it says zero ground state energy. So this energy we have to take 0, and the other has energy E. Okay, so we have to calculate this one, E square. Okay, so E square expectation value, if you calculate, you will write like this: e to power I minus beta EI. Degeneracy is 1 actually. Okay, so summation E square, okay, summation on I and divided by here there will be z. Okay, this is partition function. Okay, similarly if you calculate E average, you will get here summation on EI and e to the power minus beta EI and divide by z. Okay, so here we have to calculate E square by E average square. So if we calculate E square average divided by E average square, we will get here summation E I square or e to the power minus beta EI and divided by, when you do square of this, you get something like this, summation EI e to the power minus beta EI, its whole square. And since there will be z square, so one z will come in the numerator. Okay, something like this. So now let's sum it over. So here, when we sum over all energies, we are going to get ground state energy is 0. So we'll write 0 here. So it will become 0. So 0 plus, when you write E, you get here E square e to the power minus beta E. Okay. And here you get 0 when you put E equal to 0 and plus e to the power minus beta E whole square and Z. So Z is basically e to the power minus beta E. Okay, so Z we write like something like this. See, Z is equal to e to the power minus beta EI and summation on I. So when you put 0 here, you get 1. So let's write here directly. So there is Z term. This Z term gives us 1. Oh, sorry. So 1 plus e to the power minus beta E. This we get. Okay. Summation on energy we have to do. Okay. So now let's see. This becomes e square cancel out, e to the power minus 2 beta E, take it to numerator. So you get here e to the power, this is e to the power beta E, and here 1 plus e to the power minus beta E. Okay, so let's multiply. So this becomes 1 plus e to the power beta E. That's what we have. Okay. So now see, this is finite. If you put e equal to 0, then you are going to get 2. But here e is actually greater than 0. So this term is more than 1. Okay. But so lowest minimum value jo iska aa raha hai, minimum value for this ratio is alpha. So alpha minimum is actually greater than 2 because e is not 0. But if you take alpha maximum, see, E can be higher and higher. It can be anything. Okay. So if E tends to infinity, see, if E tends to infinity, this will become infinity. So alpha tends to infinity actually. So this can be tending to infinity. Okay. So this is infinity actually. So E max is tending to infinity if E tends to infinity. So that therefore we can say that alpha lies between 2, it is greater than 2, but somewhat less than infinity. Okay. If we say that E is not infinity, it is finite. Okay, then we'll have to say that E is very large, but less than infinity. Okay, so that's the correct answer. So therefore, this answer is correct. Okay, let's move to another question. This is a question from electronics, which will be discussed by Amit sir at the end of this video. Now this one. See, the question says a faint star is known to emit light of a given frequency at an average rate of 10 photons per minute. So question is, an astronomer plans to ensure this rate using photon counting detector. She wants to measure the rate at an accuracy of 5%. So approximately how long should be the exposure time? How long should be the exposure time? Okay, so that's the question. So actually see here, question is here accuracy, that means error is given. Okay, this error is given. We can say error is equal to 5%, that means 0.05. Okay, that is error. And how long, suppose suppose duration we have to find for how long measurement should be done. Okay, duration is equal to what? So suppose I say that duration is t minutes. Okay, so suppose I say duration is t minutes. तो इसमें जो नंबर ऑफ photons होंगे, photons detected, that will become equal to 10 into t, because for each t minutes we are taking. Okay, t minutes. So because in each minute 10 photons are being detected. Okay, so number of photon will be 10 into t. So either we can do like this. Suppose we calculate number of photons detected. Okay, then we can put number of photon detected divide by 10, then you will get t. That means duration. So this is a question of detection of photon. See, suppose a photon is coming, then a detector will either detect the photon or it will not detect the photon. So this is like a binary situation. Either there is detection or no detection. So the data that we'll get from here will have a binomial nature. Okay. So in actually binomial distribution, there is a formula for error for a given um, data. Okay, given number of sample points. Okay, so there is a formula for error. Okay, error is something like this. So error in binomial distribution, this is something approximately equal to 1.96 and root under p into 1 minus p and divide by n, where n is the number of data points. Okay, and error and p is the probability. Okay, of favorable or unfavorable event. Okay, so basically in binomial distribution, suppose we say that probability of measuring the photon or detecting the photon or not detecting the photon is same, then p will be equal to 1 by 2. Okay, so here error is 0.05, it is 1.96, and therefore here you can write 1 by 2 minus 1 by 2 and n. Okay, so if from here if you calculate n, it comes out to be around 385. Okay, you can check. So it comes out to be 385. So this is n. Okay, number of photons. So if you put here 385, then t you are going to get is 38.5. Itna minutes. Okay, so that is close to actually 40 minutes. So that's the answer. So this is actually a question related to binomial distribution. Okay, so in binomial distribution, if you use this formula, then we can directly get the answer. Okay, there can be other ways to solve this question also, but I could figure out this method. Okay, now question says in in a mercury vapor lamp and electric. So there is basically mercury vapor lamp which is being used for Michelson interferometer. So what actually happens when mercury vapor lamp is switched on, it starts heating up. Okay, so initially it emits fewer wavelengths, but as temperature rises, it emits more and more wavelengths. Okay, and because of the increase in temperature also, there is some kind of disturbance. Okay, so therefore initially although intensity of light is less, okay, but few wavelengths are emitted. Okay, so that's why fringes are more clear actually. Okay, contrast is good, but when lots of wavelengths are emitted, then interference pattern actually gets blurred. Okay, so that's why first, because so the reason I have told you, because of higher temperature more and more wavelengths are emitted later on. Okay, so that's why initially interference pattern is formed because of few wavelengths only, but later on interference pattern is formed because of many wavelengths. Okay, that's why if interference pattern is formed because of many wavelengths, obviously there won't be much contrast. Okay, so in the beginning intensity was low but contrast was there, but later on intensity will be high but contrast won't be there because of the presence of many wavelengths. Okay, so therefore first option is correct actually. So this is a theoretical question. Okay, now in this question photons are passing through a lead brick. So question is actually what percentage of intensity is actually transmitted, right? See, fraction of incident photons that will lose, that will cross. Okay, कितने photons का fraction जो है cross करेगा. So actually there is a well known formula in this case. Intensity transmitted is equal to sigma and number of atoms or molecules per unit volume and thickness. Okay, suppose its thickness is d. So this is the formula. Okay, here n is actually obtained using mass density. See here, mass density is given to be this, divided by mass of one atom. Okay, so mass of one atom. So mass density is given to be 11.29, and mass of one atom, if you write, this is 207.2. This mu में given है, तो इसको kg में convert करने के लिए 1.66 into 10 to the power minus 27 से multiply कर देंगे. So we get n here. Now we have sigma. Sigma is given to be here 10 to the power minus 23 centimeter square. Okay, so you can write it as 10 to the power -4. So this will become meter square. Okay, or you can see this was also in gram. So what if you write it in gram, then it will be 10 to power -24. I think 20. Yeah, it will be 10 to power -24. So 27 I have written. So if you can convert this also into kg. Okay, this is 10 to power -3. Okay, so this is the crop. So I'm converting everything into. Acha, so let us leave it in as see this is centimeter cube actually. So leave it in centimeter. Okay, have you converted the mass unit only? Okay, I'm leaving it in centimeter cube. So this also will leave in centimeter square. So that is the sigma. This is centimeter square, and d is given to be in here. Thickness must be given 10 mm. So if you write in centimeter, it is 1 centimeter thick. So we'll put all these things here. Okay, and so all the numbers I have given to you. See, this was mass density. If you divide it by mass of one atom, you will get number density. Okay, so that's what I have done. Okay, now if you put all these things here, you will get I is equal to I naught and multiplied by 0.72. It is exactly coming out to be 0.72. I have done this calculation. Okay, so you just have to plug in this here. Okay, so that's why we'll say that 72%. So this is a transmitted intensity, which is 0.72 times the incident intensity. So therefore we can say that I is 72% of I naught. That's what we can say. Okay, all right. Now next question. See, this is a question of diffraction pattern. See, actually question says this kind of diffraction pattern can be obtained from which of these figures. Okay, so let me tell you what actually happens. See, suppose we start with this one. Okay, so if there is a diffraction pattern because of single square aperture, you get something like this. Actually, light passing through this square aperture will diffract in this direction as well as in this direction. So you will get something like this, some pattern of this kind. Okay, this side also you will get something like this. Okay, and this side also something like this. So something like this. So because of single square aperture, you get diffraction pattern of this kind, but these will be white patches. Okay, and there will be dark lines here. Oh, sorry, dark patches here. Okay, but inside this white there won't be any maximum minimum. Okay, so this is like single slit diffraction. Okay, in single slit inside this maxima we don't get any minima. Okay, but here you see inside this white patch there are also some maxima minima. Okay, so this is actually primary. This is primary maxima, and inside the primary there are also some secondary maxima. So remember, inside primary maxima, if there are some secondary maxima, okay, then that can happen only if there are multiple slits. Okay, so therefore inside this whole thing is primary maxima, and inside this primary you can see there are fine lines of maxima and minima. So that can happen only if there are more than one slit. Okay, so therefore option of one slit is not possible. Okay, so it is not a diffraction pattern of single square aperture. Okay, now another thing you see, so now it is clear that we have diffraction pattern because of more than one slit, either two or three, whatever. Now you see here, suppose, so this is a diffraction pattern of single square aperture. Okay, now light is coming from two square apertures. Suppose this is a square aperture and this is square aperture. Okay, now suppose we consider this point, and this point. So light coming from here and here will have part difference 0, and light coming from here to here will also have part difference 0. Light going to this point from this to aperture will also have part difference 0. So if there is maximum here, there will be maximum here, there will also be maximum here. So inside this, see this patch we call as primary maxima. Okay, so inside primary we are getting some secondary maxima. So you will see that in secondary maxima you will have this kind of situation. If there is maximum, there is maximum above this, there is maximum above this. Okay, so if 2 square, okay, two square aperture like this, then above one maxima there will be another maxima, there will be another maxima like this. Okay, so that kind of situation you see here is occurring. Okay, you see, if you notice any maxima, see there is maxima here, so above this there is maxima here, and above this there is also maxima here. Okay, so this can happen only with this kind of arrangement. Okay, if there are yeah, if there are two square aperture. Okay, and if you analyze this one, okay, so in this case the same thing will happen. Okay, here if you calculate part difference here, okay, you will have same part difference part difference of light coming from these two apertures, 0 here, 0 here, 0 here also. So there will be maxima. If there is maxima here, there will also be maxima here, there will also be maxima here. So okay, so one maxima after the other maxima we will get. Okay, so in this case, if diffraction pattern we get, then secondary maxima will not be vertical, but secondary maxima will be horizontal. Okay, so in this case, secondary maxima will be horizontal actually. Okay, so that's why correct option is this actually. Okay, because secondary maxima are vertical. Okay, here जैसा कि हम बता रहे हैं अभी कि if there is maxima at one place, above that also light coming from these two square aperture will have part difference 0, so there will again be a maxima. Okay, okay, one more thing we can say that here in this direction, see there in this direction, dimension of aperture, see there are two aperture in x direction. Okay, but in terms of y direction, if we talk about, so there is only one aperture. Okay, so diffraction will be more in y direction. Okay, because this side confinement is more, this side confinement is less. Okay, so spreading will be more in y direction. Okay, that's why you see that thickness of secondary maxima is very small in x direction, but large in y direction, because in x direction the width is more. Okay, because there is width here also and there is width here, but in y direction width is same everywhere. Okay, so more spreading of light will occur in y direction here. In this case, more spreading of light will occur in x direction. Okay, you can say that. Okay, but the main explanation is actually like this: if there is primary maxima and inside primary maxima there are secondary maxima also, then this is diffraction pattern because of more than one slit. Okay, and since these are oriented in x direction, so secondary maxima will be elongated in y direction. Okay, that's what is happening here. Okay, so therefore correct option is A. Now this question, see, this question is something not very appropriate. See here, actually, it says this electric field is due to traveling wave or standing wave. Okay. See here, if you put z equal to 0, then you are getting electric field equal to 0. Okay. So at z equal to 0, we are always getting electric field equal to 0. That means this is for all t. This is for all t. So therefore, this can be possible only if it is a standing wave. Okay, this is what actually happens for a standing wave. Z equal to 0 पे हम लोग electric field 0 मिल रहा है. That means this is node. Okay, this is node. So therefore, this is it is quite confirmed that it is a standing wave. Okay. Now question is, it is left circularly standing wave or right circularly polarized standing wave. It is quite clear that it is standing wave. So either option A or option B is correct. Now it says it is left circularly or right circularly. See, left circularly and right circularly polarized, when we talk about, it is a convention, and that convention has to be specified, because suppose I call it left circularly polarized light, then some books may call it right circularly polarized light. Okay, so unless we specify the convention, which convention we are using, okay, we cannot tell whether it is left or right circularly polarized. So since convention is not given, so therefore this question is not correct actually. Okay, now let's move to this question. See, it says minimum energy required to dissociate hydrogen molecule into atoms is 4.5 electron volt. If electron affinity of hydrogen atom is 0.75, the minimum energy required to dissociate hydrogen molecule into hydrogen plus and hydrogen minus. See, what happens? We have hydrogen molecule. Now we dissociate into two hydrogen atom. So here we actually give energy of 4.5 electron volt. Okay. Now from here, what we do is we remove one electron. From here we remove one electron. Okay, so in this case also we give 13 point, if you want to remove one electron from a hydrogen atom, you have to supply 13.6 electron volt energy. Okay, now if you transfer this electron to another hydrogen atom, okay, so you are adding this electron to another hydrogen atom. So because of electron affinity, it releases energy of 0.75 electron volt. Okay, so therefore energy required for this process will be 4.5. We are giving 13.6, we are giving, but we are recovering 7.5 electron volt, 0.75. So that is the energy. Okay, so if you add all this, you get 17.35 electron volt. Okay, now this one, it says binding energy formula is given, and we have to find mass difference between two mirror nuclei. These two are mirror nuclei. Okay, so for mirror nuclei, see, A is 13 for both, so therefore A dependent term will cancel out. Okay, if we take difference in binding energy, only Z dependent term, Z is different. For one, Z is 6, and for the other, Z is 7. Okay, this term, you see, A minus 2Z, A minus 2Z, if you see, A is 13 and Z, sorry, 13 and minus Z is 6. So this comes out to be 1, and A is 13 and Z is 7. So this comes out to be minus 1. But since it is square, okay, so therefore ये square है, तो इसलिए हम लोग, okay, here since it is a square, so we will get here plus 1. So again, this term will also cancel out. Okay, so this term will, so only this term will survive. Okay, so we write mass of suppose we write this one carbon. Okay, then we'll write in carbon we have 6 proton plus 7 neutron. Okay, 7 mass of neutron minus, we'll get some binding energy of carbon. Now if we write mass of nitrogen, we will get, for nitrogen we have 7 proton and 6 neutron and minus binding energy of nitrogen. Okay, so let us take difference of the two. So if we take difference, we will get mass of nitrogen minus mass of carbon we are calculating. So mass of nitrogen minus mass of carbon, if you calculate, see, actually nitrogen has more number of, let us calculate, see whatever positive negative it comes. So this minus this, if we calculate, we get mass of proton, and here minus mass of neutron. Okay, that's what we are getting from here. This is more actually. So and plus binding energy of carbon minus binding energy of nitrogen. This is what we have. Okay, so mass of proton minus mass of neutron is close to 1 mega electron, minus 1 mega electron volt. This will give, this we can check, data must be given, okay, in the beginning of the question paper. Okay, so from there we can check. So now these two differences we have to calculate. So for carbon, if you put here, see here we have binding energy of carbon. So carbon 6 minus 5, we get here 30. So we get here minus 30 or divided by into AC or divided by A2. For carbon we have, so this is 13 to the power 1 by 3. Okay, for carbon we get. For nitrogen we get here 7 into 6, 42. So we'll get here 42 AC, because this is, there is negative sign, negative and negative will become positive. 42 AC and divide by 13 to the power 1 by 3. So we are getting here basically this is 12 AC. You take difference divide by 13 to the power 1 by 3 and minus 1 mega electron volt. Now let's put the value. So 12 and here AC. AC is given to be 0.7 and divide by 13 to the power 1 by 3. Okay. And minus 1 mega electron volt. This we get. I think this is what we are getting. Okay. So if you multiply, you get 8.4 or divide by 13 to the power 1 by 3 minus 1 mega electron volt. I think we are getting this answer. Okay, so you can just calculate. I haven't done this calculation. Let's see what we are getting. So we have 8.4 divided by 13 to the power 1/3. Yeah, so we are getting 3.57, and that is minus 1. Okay, so this is basically 3.57 we are getting from here, and minus 1, so you will get 2.57 or something. Okay, so approximately this is the closest answer that we are getting. Okay, option A. So option A is the correct answer. Okay, 2.57 mega electron volt. Okay, mega electron volt. All right, next question. See this question from relativity. It says a particle. See this line, ये जो dotted line है, this is actually x equal to ct line है. This is x is equal to ct line. Okay. So from here, if you calculate dx by dt from this equation, dx by dt, then you will get c. That means for this line, slope is equal to c है. Okay. Slope. So slope is actually velocity. Dx by dt is velocity. So basically, we can say that this line is for photon. Okay. Here velocity is equal to c. But for it says a relativistic particle moving in one dimension, x starts from x equal to 0 and is subjected to uniform constant force. So in this case, for particle, ये जो है ना for photon है, this is for photon. So this dotted line is made for photon. Okay, for particle, if we see particle, dx by dt will be equal to actually velocity of the particle, which is generally equal to c. But at t equal to 0 in the beginning, at t equal to 0, it was dx by dt is 0. In the beginning, it was at rest. So therefore, slope is 0 actually. Dx by dt here, x versus t graph we are plotting. So slope is 0. Slope is 0. That means graph will be parallel to x-axis. So graph has to start parallel to x-axis. Okay. So it will be something like this. See, this is x versus t. So graph will start parallel to x-axis, something like this. Okay. Something like this. It will start parallel to x-axis like this. Okay. Now, as time passes, okay, what will happen as t goes to infinity, since particle is being acted upon by a constant force, so its speed will continuously increase. Okay, so at t goes to infinity, we will approach c. So if therefore we'll say that dx by dt will approach c. So if dx by dt is approaching c, that means the graph will become parallel to this line. Okay, because for this line, slope is equal to c actually. Okay, so that's why you see here in this graph, this solid line is starting parallel to x-axis, so therefore slope here is 0. That's what we wanted here. In the beginning, velocity is 0, so slope has to be parallel to the graph has to be parallel to this horizontal axis, time axis. So it is starting parallel, and then as time increases, it is becoming parallel to this line. Okay, it is becoming parallel to, okay. So therefore this option is most appropriate. It is not becoming parallel, you see here. Okay, and see, actually, if somebody says that this is also becoming parallel, suppose it also becomes parallel to this dotted line, then see, we will have to argue like this. See, photon has suppose traveled for time t, then it has covered a distance ct. Okay, distance covered by photon will be ct. But since initially particle had a smaller speed, so distance covered by particle will be actually smaller. Okay, so even for longer time, very long time also, if you calculate for a very long time for this t, if you calculate distance covered, so this will be distance covered by the particle. Okay, this value, and this will be distance covered by photon. Okay, so actually distance covered by the particle, ye x for particle hoga, and this will be x for photon. Okay, So distance covered by photon will always be greater than distance covered by the particle. Okay, so that's why this graph has to be correct. Okay, because this graph is ultimately touching this dotted line. Okay, so therefore according to this graph, for after a long time, distance covered by the particle and photon will become equal, but that is not true, because photon has been moving with speed c, so distance covered by photon will always be greater than distance covered by the particle. Okay, so that's why this graph has to be true. Speed may become equal, okay, but distance will still remain smaller for particle. So that's why option A is correct. Okay, now let's move to section B. Section B, here it says there is a random variable, uh, random positive variable x. It has distribution this, so we'll write like this. Just let me change the pen. So we can write p of x is equal to some k e to the power minus lambda x. Now question says probability of observing event x more than 3 average x. So let us calculate average x first. So average x will be equal to x multiplied by this probability, and since it is not normalized, so here we'll have to divide by this p of x dx. Okay, 0 to infinity. Okay, so we can integrate it. Okay, you do this integration, since this is something like radioactive decay. So if you calculate this average, it will come out to be 1 by lambda. Okay, in radioactivity also we get half mean lifetime equal to 1 by lambda. Okay, so it will come out to be, you can just do this integration and check. Okay, so therefore now probability, question says probability of observing an event x greater than 3x. So probability will be equal to, actually now, from 3x to infinity. So here we are taking allowed values of x to be greater than 3 times the average value. Okay, so here it will be p of x and dx. This is the probability. Okay, and since it was not normalized, so again we'll divide by here p of x dx and 0 to infinity, something like this. Okay, so let's see what we get. So let's put the value. So when you put this here, k will cancel out, and we get here 3 by lambda. We have x average is 1 by lambda. Okay, to infinity, and here we have e to the power minus lambda x and dx, and here we have e to the power minus lambda x and dx and 0 to infinity. This is just normalization factor. Okay, so now here when you integrate, you get minus 1 by lambda here, lambda here also, so those factors cancel out, and you get here e to the power minus infinity when you put upper limit, and minus e to the power minus when you put lower limit, lambda cancel out, you get minus 3, and here you get e to the power minus infinity and minus e to the power 0. Okay, so therefore this term becomes 0, so you get here 1 by e cube with negative sign, and here you get minus 1, so therefore 1 by e cube is the answer. Okay, correct answer is this. Okay, now this question, see, I have already solved when this examination was held. Just next day I had solved this question and uploaded its solution on YouTube. I'll put its description in sorry, its link into the description, so you can watch its solution in another video that is uploaded there. Okay, this question also I have solved in detail. Its solution is also uploaded. So its link also I'll provide in the description. You can check there. Okay. Now this one, see, it says there is particle coming, and this is a spherical planet, and because of the interaction, the time period of revolution of the planet changes. You can read the question. Okay, so what I'll do is I'll apply conservation of angular momentum here. Okay, L initial equal to L final. Okay, so initially, if you write angular momentum of this whole system, for this one, see, this is a line of momentum and this is a perpendicular distance. So angular momentum will be in linear momentum mv1 and r1, and its angular momentum will be minus I and omega 1. Okay, it is rotating in opposite direction. Okay, now later on, its angular momentum will be mv2 and r2, and angular momentum will be I omega 2. Okay, it's suppose angular velocity has changed from omega 1 to omega 2. Now bring it to this side. Let's say we are writing M taking it to this side. So M V2 R2 minus V1 R1 is equal to I will be common, and here you will get omega 2 minus omega 1. I'll bring it to this side. Okay. So this is solid sphere. So 2 by 5 M, and its radius is R square. And this will be 2 pi by T. So we'll get here 1 by T2 minus 1 by T1 and 2 pi. Okay. And here we have this term M and V2 R2 minus V1 R1. Okay. So now you take LCM here, 2 by 5 M into R square. And here you get T1 minus T2 and divide by T1 into T2 and 2 pi. So now we can calculate from here T1 minus T2 will be equal to, just do cross multiplication. So you get here 5 small m and V2 R2 minus V1 R1, and here T1 into T2. Okay, T1 into T2 and divided by, you get 4 pi capital M or into R square. Okay, now suppose this is the time difference delta T we are getting from here. Okay, and in place of T1 and T2 approximately we are writing T. Okay, so therefore we'll get here 5 M, and here V2 R2 minus V1 R1, and here we get T square and divide by 4 pi M into R square. That's what we get. So therefore correct option is option A. Okay, option A is the correct option. This is a question from quantum mechanics. See, the question says uncertainty. This is a particle in a box in ground state. So if you write its wave function, you get psi equal to root under 2 by L and cos pi x divided by pi x by L. This is what you get. Okay, that is the ground state wave function. Okay, see, this potential is symmetric, therefore x average value of x will be 0 and wave function is real, average value of px will be 0. Okay, now energy, we know that if you calculate px square by 2m, okay, that is equal to energy for ground, we write energy as n square pi square h bar square upon 2m L square. So for ground state n equal to 1, so we get here pi square h bar square upon 2m into L square. So therefore 2m will cancel out. If you calculate px square, we get here pi h bar upon L. So that is actually expectation value of px square. Okay. So from here we can calculate uncertainty delta px. Okay, delta px. So that is equal to root under px square average minus px average whole square. Okay, sorry, here there is pi square h bar square L square. Okay, pi square h bar square upon L square, 2m got cancelled. Okay, so here if you put px square average, you get this, and px average is 0. So you get here pi h bar and divide by L. Okay, now x average is 0, we can calculate x square average. X square average will be equal to psi star x square and psi and dx. Okay, from minus L by 2 to plus L by 2. Okay, you can calculate this. This comes out to be, see, this integration we can just put here and get the value. Okay, so let me see, this will come out to be, I have perhaps written somewhere, let me check. Yeah, so in general, it comes out to be this much. L square, if you calculate this x square average comes out to be L square, and here 1 by 12 minus 1 by 2 n square pi square. Okay, this is what you get, x square. So for ground state n equal to, we'll put 1. Okay, so here we'll put 1. That's what we have. So therefore now you calculate delta x. So delta x is x square average minus x average whole square. So this will become L root under 1 by 12 minus 1 by 2 pi square. So that is delta x, and delta px. Okay, delta px is this much. So if you multiply these two, ठीक है, delta x and delta px. L will cancel out, you will get here pi into h bar and root under 1 by 12 minus 1 by 2 pi square. ये आ रहा है, ठीक है. So you can calculate this. Okay, this point, it comes out to be 0.56 h bar. Okay, so definitely this is greater than actually h bar by 2 and less than h bar. So this delta, we can say that this is greater than 0.5, but this is less than h bar. So delta x delta px is less than h bar, but it is greater than h bar by 2. Okay, that is the answer. All right, so this is quite calculative question. Okay, now this one, it says, yeah, this is the potential considered diatomic molecule. So in diatomic molecule, these are the masses. So we'll calculate reduced mass like this, m1 into m2 or divided by m1 plus m2. So that is given to be 8 into 1 divided by 9 hoga mu. So atomic mass unit, you can convert this. So this is 8 by 9, or since your answer is given in SI unit, so 1.66 into 10 to the power minus 27 kg. You can write like this. Okay. Now potential is of this form. So there is diatomic molecule. Okay, and this molecule is vibrating. Okay, we have to calculate its frequency of vibration. Okay, vibrational frequency corresponding to vibrational spectrum. Okay, so frequency is actually written like this. Angular frequency is written like this: force constant or divided by reduced mass. Okay, so nu will be equal to 1 by 2 pi and force constant and divide by reduced mass. So reduced mass is this. Okay, now to calculate force constant, first of all we'll calculate equilibrium length. Okay, equilibrium length. For that we'll put dv by dr at some equilibrium. R naught is equilibrium length. Okay, this is equilibrium length of the molecule, so that is equal to 0. When you differentiate it, see here you get minus a power 4 and divide by r naught to the power 5, you will get here, and here you will get plus b square or divide by r naught to the power 3. So therefore, from here you get r naught square is equal to a to the power 4 by b square. To calculate from here, this is equal to 0 here. ठीक है ना? First derivative for this is for equilibrium length. R naught is equilibrium length. Okay, so r naught square we have gotten this. Now force constant is actually, this force constant k is actually second derivative of potential energy dv by dr square at r naught at equilibrium length. Okay, r naught is equilibrium length. So now differentiate it once more, you will get here 5. There is epsilon term here. Okay, you will get here 5 a to the power 4 by r naught to the power 6 minus, okay, here you will get 3b square by r naught to the power 4. Okay, so you can take epsilon by r naught to the power 4 common, and here you will get 5 a to the power 4 divided by r naught square and minus 3b square. That's what you get. Now you put r naught square here. So a power 4 will cancel out. You will get b square in the numerator. So 5 minus 3, it will become 2. So it will become 2 epsilon naught and a power 4. Sorry, a power 4 got cancelled out. We got here b square and divide by, we are getting r naught to the power 4. So now put the value of r naught square here. Okay, so this is 2 epsilon and b square. And when you put this r naught power 4 here, it will become a power 8, and here b power 4 will come in the numerator. So it is 2 epsilon and b power 6 or divided by a power 8. That is the k. Okay. So this is the value of k, and so therefore nu we can calculate 1 by 2 pi and root under k. So this k we have to put here. Okay. So if you put this k, we get 2 epsilon b power 6 by a power 8 and here mu, this reduced mass. Now you have everything given here. See, a is given, epsilon is given, a and b are given. Yeah, atomic mass is given. Sorry, so mu, reduced mass is given. Everything is given. So you just put everything, you will get the answer. Okay. So the correct option you can check will come out to be this much. It exactly comes out to be this much. I have done this calculation. Okay. So it comes out to be this much. Next, this is a very simple question. See, here we have to calculate electric field and here we have to calculate electric field. Okay. In this case, here electric field is E1 and here electric field is E2. Okay. So even if you calculate, you know that at outside point, a uniformly charged sphere behaves like point charge. So it will be simply kq by 2r whole square because it is at a distance 2r. Okay. Now here, if you calculate electric field because of this point charge will be in this direction. Because of this, it will be in this direction. Okay. This distance is r. This distance is 2r. So this distance will be root 5r. Okay. So here field will be kq. Q in place of q we have q by 2. Okay. And divide by distance square. So root 5r whole square. Okay. Here also we'll get same thing, k q by 2 and root 5r whole square. That's what we get. Now let's say this angle is theta, so this angle will also be theta. So we'll take its cos component. So here E2 jo niklega, okay, E2 will be equal to kq by 2 and divide by root 5r whole square and 2 cos theta. Okay, cos theta from here and here we'll get. Okay, so we are getting 2 and 2 will cancel out, so we'll get kq by 5r square. Okay, and cos theta, if you calculate from here, cos theta will be b by h. So this will be here 2 by root 5. That is the value of cos theta. So this is E2. Now we have to calculate E2 by E1. See, this is E1. So if you calculate E2 divided by E1, see what we are getting. All the common factors will cancel out. In E2 we have 2 divided by 5 root 5. In E2 we have this. In E1 we have basically 1 by 4. So it will become 4 by 1. Sorry, 4 by 1. Okay. So therefore 402 8 divided by 5 root 5 we get. Okay. That's the answer. So again, this option A is correct. Now, this question, see in this question, it says a small satellite has a rectangular solar cell of dimension 4. So this is 4 and this from here to here also this is 4. Okay. Which propels the satellite upon receiving light. One of the cell is perfect reflector while the other is perfect absorber. Okay. So question is assuming uniform sunlight incident normally on the cell and with an intensity is given and ignoring the satellite shadowing effect, the instantaneous torque we have to calculate. Suppose light is falling perpendicularly like this. On this portion light is falling like this and on this portion also light is falling like this. Okay, light is falling perpendicularly on both sides. So it is so we have to calculate basically torque. So let us calculate force. Okay, so force, if you calculate, force is actually equal to power by c. Okay, if light is perfect fully absorbed. Okay, so power is suppose p, power see intensity is given, so we can write power is intensity into area. A is area or divided by c, so that is the force. Okay, so here force on this will be since it is getting reflected, force on this will be twice actually in this direction in inward. Okay, and force on this will be basically just if force on this is f, sorry, on this is f, then force on this will be 2f. Okay, it is something like this. Force on this is f, then force on this will be 2f. Okay, because here light is getting reflected, so force double force will act on it. Okay, because of reflection, momentum imparted becomes double. Okay, so if force here is f, then force here will be 2f. Okay, so it is something of this kind of situation. See here, suppose we have a rod and suppose we apply a force f here and a force f here, 2f here. Then if you calculate torque about this point, then torque because of this will be force into distance and it will be also force into distance. So torque of the two will be opposite in direction. So if you calculate torque about center, it will be suppose this distance is d and this distance is also d. Then torque here will be only f into d because torque of this and this will be in opposite, will have opposite sign. Okay, so subtraction ho jayega, there will be subtraction of the torque. Okay, so torque if you calculate here, okay, see, in this situation torque will be actually equal to force into distance. So actually at center, we'll say effectively force is acting, so distance will be this much only. Okay, so let us write IA and divide by C, and distance we'll write. Okay, this we are calling distance. So let's put the values. Okay, so here you see, um, torque is equal to I intensity is how much, 1370, and area, this much area individually we are calculating for this portion and this portion, so area will be 16. Okay, and C is 3 into 10 to the power 8, and D will be this much. Okay, so 2, that's what. So you can calculate this. Okay, so you calculate, you will get the first option. Okay, torque will come out to be this 1.46 into 10 to the power minus 4 Newton meter. It exactly comes out to be this much. Okay, so that's what the answer is. Okay, so you can check the calculation. Okay, now let's do this question. It says equilibrium temperature T naught on the surface of planet results from balance between energy received from the host star. See, the situation is something like this. Energy received from host star and the energy they emit back into the space. In case of Earth, see, suppose this is sun, okay, and this is Earth. So light from sun is falling on Earth, okay, and Earth is also emitting light in space, like black body, okay, something like this. Now question is, in case of Earth, its temperature is T naught. T naught, that is equal to 300 Kelvin. Now there is, so suppose sun is sending power, suppose P. Sun is sending a power P, okay, in all direction. Okay, it is sending in all direction actually. ये distance suppose करो R है. Now there is a star, faint star बोला गया. There is faint star. Now consider an exoplanet of the same size as Earth, which orbits a faint star. This is faint star. So this faint star is sending some power, which is P by 4, which is sending power 25% of the sun. Okay, and this is some exoplanet. Exoplanet. So this has same radius as Earth. Earth has suppose radius R, then this also has radius R. This distance here to here is actually R by 4. The question, that's what question says. In almost orbit of the radius 25% that of the Earth sun distance. So here to here distance is R by 4. Okay, that is the situation. So sun to Earth distance is R, then this distance faint star to exoplanet distance is R by 4, and faint star is emitting a power P in all direction. Okay, in all direction it is emitting power. So this is P by 4. All right. Now question says, iska equilibrium temperature T naught primed hai. So this T naught primed we have to find if Earth's equilibrium temperature T naught is 300 Kelvin. Okay, so let's see how we can do it. See, this sun is emitting power P. That power is spreading in a wavefront of radius R when it is falling on Earth. So intensity we will calculate. Intensity for sun Earth के लिए पहले calculation कर रहे हैं. Sun Earth. So intensity will be equal to power divided by 4 pi R square. Okay, so energy falling on Earth. Energy falling on Earth. So that will be equal to, or power, let's say, power falling on Earth. Energy falling, yeah, energy भी लिख सकते हैं. Energy falling on Earth per second. Per second. Okay. So if you calculate, you'll have to roughly multiply by area of front's cross section. Okay, so roughly we can write it as energy is equal to P upon 4 pi R square and pi R square. That is the cross section area of Earth. Okay, pi R square roughly we have written. Okay, now for exoplanet, if we write for But see, Earth is actually receiving this much energy, and it is also emitting energy like black body. So therefore, this must be equal to sigma T naught to the power 4. That is P upon 4 pi r square and into pi capital R square. So call it equation number 1. It is emitting like black body. So using Stephen's formula, we have written this. Okay. Now for faint star and exoplanet, if we write for this, okay, then we have this kind of situation. C T naught prime to the power 4 is equal to, here power is 1 by 4, P by 4 and 4 pi, and this distance is R by 4 whole square, and its area is same as Earth area, so this factor will remain same. So let us divide these two. Okay, so we'll get here T naught to the power 4 divided by T naught primed to the power 4 is equal to, here we will get, you see, 4 and multiplied by 6. Other factors will cancel out. Okay, so we'll get here 4 to the power 3 actually. Okay, 2 4 from here and 4 1 4 from here. So we are going to get, that's what we are getting, right? No, actually we'll get 1 by, because this is in denominator. Okay, no, I made a mistake, I think. We'll get here one, this here from here, we are getting 4 square 16 and 4, so these 4 will cancel out, so we'll get here 1 4 in the numerator only. 1 4 will be there. Okay, yeah, that's what we get. So therefore, where are we getting? Wait just a minute. This, so 1 4 will come in numerator, and since we are dividing this, so sorry, 1 4 will get in denominator. Okay, you can check this. Okay, this is just a basic calculation. So therefore, we are getting T naught primed is equal to 4 to the power 1 by 4, and here T naught. That's what we get. So here, this is 4 to the power 1 by 4. So basically, this is, we can write it like this. This is root 2 into T naught. Okay, so T naught primed is equal to root 2 is 1.414 and multiplied by 300. Okay, so we can multiply it. This is what we are going to get. Okay, so 424.2 we will get. Okay, so answer is 424 Kelvin. Okay, that's the correct answer, this one. So option A is coming out to be correct, 424. All right, now next question. This is an electronics question which will be discussed at the towards the end. This will also be discussed towards the end. Now this is a question from diffraction. It says diffraction grating spectrometer is used to resolve 2 sodium lines. एक का wavelength दिया हुआ है 5890, the other wavelength is 5896. So question is 589.6 nanometer in first order diffraction. Okay, so if the width of the grating is 2 centimeter and the focal length of the spectrograph camera is 20 centimeter, what the linear separation at the focal plane of the 2D lines will be? Linear separation we have to calculate. So let us calculate diffraction angle. See, we'll write d sin theta 1 is equal to, फर्स्ट ऑर्डर है तो एन लेमडा जो हम लोग लिखते हैं ऐसे लिखते हैं ना, डी साइन थीटा, वी राइट लाइक दिस, डी साइन थीटा इज इक्वल टू एन लेमडा फॉर डिफ्रैक्शन, एन लेमडा, so first order, so here we'll write lambda 1, and since lambda is in nanometer and this slit width is a small, so lambda is actually small, we'll assume this angle to be small, so we'll write theta 1 is equal to lambda 1 by d. Okay, similarly we'll get theta 2 is equal to lambda 2 by d. Okay, so difference in the angle will be equal to delta lambda by d. Okay, so d is the grating element. Okay, so d is grating element, which is written like this, d is equal to width by number of lines. Okay, but here number of lines is not given, so let us assume that this grating is just able to resolve the uh, two wavelengths. Okay, so therefore delta lambda by lambda will be equal to n into m. Okay, so m is the order, or small n, let us write here capital N into n. So for first order, in first order it is resolving, so n will be equal to 1 here. Okay, so delta lambda by lambda will be equal to n. Okay, so in place of n we can write this. Okay, so let's see what we get. So therefore d will be equal to width divided by n. So width is given 2 centimeter and n we have gotten delta n, delta lambda into lambda. Okay, so that's the d. So therefore delta theta will be equal to here we have delta lambda and divided by d. So d is actually w and by lambda and delta lambda divided by delta lambda, so it will become delta lambda square. Okay, so delta theta is coming out to be this much. Okay, so now it is something like this. Suppose this is the grating and here d1 line is observed, here d2 line, here d2 line is observed, here d1 line is observed. Okay, so this angle is basically delta theta. Now this length is focal length. Okay, so this linear separation we want to calculate. Suppose this is y, so obviously y will be equal to f into delta theta. So this is f and delta theta is delta lambda whole square and divided by w into lambda. Okay, so you can just put all the things that is given. Okay, width is given, lambda is given, and difference is given. Okay, if you do this, okay, you will get first option. Okay, you can check here, you can calculate and check. Okay, so I'm leaving that calculation part. Okay, so what we did, we just used diffraction condition. We calculated angle of diffraction for the two wavelengths and we took the difference. So difference is this, actually one spectrum is coming here and the other is here. So this is the angle of difference in angle of diffraction. Okay, so but d was not given, d, and for that we needed n. Okay, so that's why we use this formula, delta lambda by lambda is equal to n into n. Okay, so from there we can get the value. This is first order diffractions, we have put n equal to 1. Okay, so you can just do the calculation and see, you will be getting option A. Okay, now this one, see here a photon is interacting with an electron. Okay, so it says it has initial speed ui. let's write like this. It has initial speed ui. Let's say it has initial speed uf or vf, whatever we write. Of its frequency is nu I. Its frequency is nu I and its frequency, suppose nu f. Okay, now question is initial momentum of electron kitna hai yahan pe. Now question says here, see a photon of frequency nu I collides head on with an electron of mass m having speed u, and the photon scatters off in directly exactly opposite, sorry, in direction exactly opposite to its initial momentum. It is found that frequency of scattered photon is same as that of अच्छा ये nu f जो है ना final frequency is same as nu I, ऐसा दिया हुआ है. So let us apply conservation of momentum. We are applying conservation of momentum and energy. Okay, so we'll write here p initial sum should be equal to p final sum. Okay, so p initial sum, if you write for photon, you will write h nu I by c. For electron, we'll write m ui. Okay, for photon it is going in opposite direction, so now we'll write h nu I because final frequency is same as initial by c, and for photon for electron we'll write m uf. So bring it to this side, so you get here 2 times h nu I divided by c. Frequency is given to be same, so for final also we are using same frequency, is equal to m, and here you get ui plus uf. This is first equation. Okay, now let's use conservation of energy. So we'll write sum of energy initial is equal to sum of energy final. So energy, if you write energy of photon is h nu I, or energy of this electron will be equal to some gamma m c square. Okay, m naught c square, like mass of electron. Now here final energy will be again h nu I because frequency is remaining same, and this is gamma I, let us write, and this is gamma f. Speed is different, so this is gamma f, and m naught c square. See, this term will cancel out, m naught c square will cancel out, so therefore we conclude that gamma initial is equal to gamma final, and gamma can be same only if u initial is equal to u final. तो यहाँ से conclusion आ रहा है, since gamma is coming out to be same from here, so speed is also same. So now put into 1. Okay, so if we put into 1 here, u in place of u final, we'll write u initial. So we'll get m into u initial 2 times. Here we'll get 2h new initial and divide by c. So 2 and 2 will cancel out. So m into u initial will be equal to h new initial and divide by c. So therefore, momentum of electron, initial momentum of electron is equal to h new. So that is the correct magnitude of initial momentum of electron is this much. So this is the correct option, option A. Okay. Now this is a question from hyperfine splitting. It says a number of hyperfine states are found in helium atom for electronic configuration. Number of hyperfine states we have to calculate. See, there are 2 unpaired electrons. So let us write S for S1 is half, and for this electron also S2 will be equal to half. So if you calculate S from here, it will be from S1 minus S2 to S1 plus S2. So it will be 0 and 1. Okay. Now for this electron, L1 is equal to 0 hai, and for the second electron, L2 is 1. So therefore, if you calculate L1 minus L2 to L1 plus L2, so that is 1 actually. Okay. So now let us calculate J. So J we are calculating using S equal to 0 and L equal to 1. So if you calculate this J, you will get here L minus S to L plus S. So that is only 1. Okay. Now see, there are actually question is related to helium-3. So there are 3 nucleons. Okay. So if you calculate nuclear spin, so 2 electron will be paired, 2 nucleon will be paired, only 1 unpaired electron is there. So I will be equal to 1 by 2. Okay, because of 1 unpaired nucleon. Okay. So therefore, all right, so this is the situation. So now let us calculate F here. F. So here J is equal to 1 we have. So F will is actually, we write J minus I to J modulus J plus I. So if you calculate J minus I, see I is half and J is here 1. So 1 minus half to 1 plus half. So you will get here 1 minus half is half and 1 plus half is 3 by 2. So there are 2 values of F we are getting. Okay. So we have gotten 2 F states now. Okay. 2 hyperfine states. Now let us calculate J using S equal to 1 and L is equal to 1. Okay. This S equal to 1. We have used S equal to 0. So here, if you calculate J, L minus S to L plus S, so you will get L minus S 0 and L plus S 2 aega. So this will be 0, 1, 2. Okay. So this is J. Now, if we calculate F, so F will be equal to, again, J minus I to J plus I. So J, if I use J equal to, see here, if I use here J equal to, let's write like this. See, if I use J equal to 0 and I equal to half, then I get here, J was only one value. Now here we have 3 values of J. So I'm using J equal to 0 and J equal to I equal to half. So this will give you half only. Okay, because J minus I to J plus I. Now if you calculate F equal to J equal to here 1 and I equal to half, for these states that we are calculating here. Okay, for this state we have already done the calculation, so we got 2 F states. Okay, so here again J minus I to J plus I, so you will get here half and 3 by 2. Okay, now if you calculate F with J equal to 2 and I equal to half, then again J minus I to J plus I, so 2 minus half, that will be 3 by 2, and 2 plus half is 5 by 2. So you got 2 states. So here, now let us count the number of states. See, here we are getting, just a minute. Here we are getting 2 states. Oh, sorry. See, here we have gotten 2 states, F equal to half and F equal to 3 by 2. These are 2. It says number of hyperfine states. So we are getting 2 hyperfine states here. Okay. Here we are getting one state. Here we are getting two states. And here we are getting two states, two values of f. So total you get, you see, you get 2 plus 2 plus 2, 6 and plus 1, 7. So 7 hyperfine states. That's what we get. Okay. Now this one, this is a question from solid state physics. Okay. It says here first order Bragg reflection is being observed at 30°. So here, if you write d sine 30 is equal to first order diffraction is, so we write n lambda. So n is 1 and lambda. Call it its first equation. बाद में when you compress it, it becomes d primed, and we have to find the angle sin theta prime. Sin theta, let us write that is first order diffraction के लिए lambda. So basically these two are same. RHS is same, so LHS will also be same. So let us equate the two. So d will write like this: d sin 30 is equal to d primed sin theta. So sin 30 d is written like this: root under L square plus M square plus N square for cubic crystal. Okay, so this is 1 square plus 0 HKL, H square K square L square we write. Okay, HKL. So HKL is 1 0 and okay. So this is the d for cubic crystal. Okay, and here we have to write d prime. So d prime we write for now this crystal won't be cubic crystal. So now if for this we'll write like this: h by a whole square plus k by b whole square plus c by l by c whole square. Okay, and here we have sin theta. So here you get a divided by root 2 or into 1 by 2 is equal to HKL is the same 1 0 and 1. So 1 0 and 1 will put, so this will become 0. A remains the same, but this becomes C becomes actually a by root 3. That's what it says, a by root 3. So we'll get here 1 by, here you will write h is 1 and this is 1 by a square, and plus this will become 0 because k, this Miller indices k is 0. Okay, and here L is 1 and divided by a by root 3 whole square. And here we have sin theta. So this becomes a divided by 2 root 2. And here we get a and divide by, here you get 1 and here you get 3. So 4, and so you'll get 2 here, sin theta. So now you see a by root 2, a by root 2 cancel out. So you get here sin theta is equal to 1 by root 2. Okay, so theta is equal to, you get 45°. So correct answer is this one. Okay. Okay, so we have completed this solution of TFR paper. Now electronics part is left. Now Amit sir will discuss solution of electronics part. Okay.